There is a shadow at the edge of everything we know. The Big Bang was meant to be the beginning, but what if it wasn't? Einstein doubted singular starts, ancient myths imagined cycles, and today's equations hint at stages before the curtain of creation ever rose. So what lies beyond? A sea of quantum foam, bubbling with particles that blink in and out of nothing. Endless universes colliding and bouncing, leaving faint scars across the sky, or a timeless state where even before and after have no meaning at all. From hidden dimensions folded in darkness to the dream of absolute nothingness, each clue pulls us closer to a mystery that refuses to be solved. Welcome to Neuro-Nap Academy, a place to drift, learn, and fall asleep a little wiser. Take a slow breath and let's wander through 101 hidden facts about what may have existed before the Big Bang. We'll begin with our first big fact. The Big Bang, as powerful and luminous as the idea sounds, might not be the absolute beginning of everything. You've been told the story like a curtain that rises on the first scene, yet physics treats that first scene as a place where our current equations stop making reliable promises. The singularity is less a crisp starting gun, and more a sign that the map you're using has run out of ink at the edge. That alone changes the tone of the entire narrative, because if the Big Bang is not the beginning, you're invited to ask what kind of stage existed before the lights came on. And here's a second key insight waiting to be unwrapped. Our next fact begins now. Even the theory that most successfully explains gravity on cosmic scales was never intended to declare a hard birth. General relativity, the framework that bends space and time, predicts its own breakdown at extreme densities. Many of its most elegant solutions aren't first moments, but entire geometries, like endless fabrics without hemming. When you hear that Einstein disliked abrupt singularities, you're hearing a deeper intuition that nature rarely ends explanatory lines with an exclamation mark when a comma will do. Let this open the door to our third fact, the one that nudges you to look past the edge of the screen. A growing family of models explicitly place something before the bang. Some imagine a contracting cosmos that reached a minimum size and then rebounded. Others picture a pre-existing arena where fields hummed in a silent equilibrium, waiting for a fluctuation to bloom. A few treat the Big Bang not as a birth, but as a phase change, like water becoming vapor, the same ingredients, a new regime. In every version before is not empty, it's structured enough to be interesting and simple enough to seed what followed. Now comes a fourth, quieter fact that hides in the behavior of equations themselves. Mathematics often hints at prior conditions when it refuses to terminate cleanly at time zero. When you run the universe backward with our best models, you don't just crash into nonsense, you encounter patterns suggesting continuity, a signal that something like time, or at least order, may have persisted. Cosmologists speak carefully here. It's not that the math proves a specific prior world, only that the most successful descriptions of this one are more comfortable extending beyond the boundary than dying against it. Where a naive story ends, a rigorous line of reasoning prefers to continue. Let's let a human echo stand beside the formalism for our fifth fact, because culture has long played with beginnings that are not singular, ancient cycles, golden ages, and dissolutions. Myths in which the cosmos breathes, rests, and begins again were not scientific theories, yet they foretold a style of thinking we now find in modern models. You don't accept a legend as data, you notice that the human imagination kept circling the same coastline. Beginnings feel less like points and more like thresholds. That intuition doesn't prove anything, but it harmonizes with the direction our best questions are already moving. If you gather those 5 facts into your hands, a shape appears. The Big Bang may be a threshold event, general relativity resists being a book with a first page, multiple frameworks propose pre-bang structure, the equations whisper continuity, and human stories have long suspected cycles. Each thread pulls on the next, and a cliff forms, because if a threshold existed, what exactly moved across it? What substance or rule could rest quietly before, and yet be capable of igniting the expansion we measure today? You sense that the next revelations must become smaller, quicker, and stranger, because the prelude to everything would be subtle by definition. Here is where the philosophical undercurrent helps you hold the scientific thread without tightening your grip too hard. When you hear not the absolute beginning, your mind hunts for a replacement beginning, as if the universe owed you a single first brick. But maybe the better posture is to accept layered origins, the beginning of space as we experience it, the beginning of the laws as we know them, the beginning of conditions suitable for galaxies and life. These beginnings can be staggered, and their staggered nature reduces the pressure to force them into one point. Complexity arrives slowly, foundations may be older than rooms. At the same time, you want clarity, not fog. So let another fact-like thought start forming. Notice how it begins softly. If mathematics encourages continuity, then any before must be described in terms that do not immediately collapse under gravity's weight or quantum uncertainty's tremor. That means the prelude is more likely a field than a thing, more like a rule than a rock. Think of a rule that holds whether or not anything plays the game, then think of the moment the game starts, because a fluctuation makes the rule visible. The poetic phrase, "the lights came on," becomes a technical hint. Illumination is an interaction, not an arrival of bulbs. But there's still a riddle beneath your feet. If the prelude was lawful, why launch a universe at all? If it was stable, why break the stillness with expansion? And if it was unstable, why did it last long enough to matter? These are philosophical questions that hide scientific teeth, because stability and fluctuation are not preferences, they are properties. When a rule allows little ripples, a large one can sometimes accumulate. When a medium can ring, it will ring. Perhaps the decision to expand wasn't a decision, but an inevitability of the medium itself, like a snowfield that will avalanche once a hidden gradient exceeds a threshold. Before we turn toward the microscopic stage where this all becomes tangible, rest with a simple picture that keeps the mystery sharp without blurring it. The Big Bang is the visible line where many narratives on our instruments begin. Your 5 initial facts suggest the line is a seam, not a wall. On one side of the seam, particles form, forces differentiate, and the cosmic background cools. On the other side, hinted at by math and by models, something quieter holds the possibility of a universe the way soil holds the possibility of a forest. You don't yet know its texture, only that it must be fine-grained and restless enough to matter. So let the next doorway open with a promise, whispered in plain language. Here comes another fact. The smallest description we possess of reality says that emptiness is never truly empty, that even nothing flickers with brief borrowed activity. If a prelude to the Big Bang existed, it would likely live there in that sea of flicker, and that means the path forward will not be found by staring at grand arcs alone, but by listening for the fizz at the bottom of the cup. The next section descends into that fizz, where vacuum reveals itself as a crowded, lively stage, and beginnings look like ripples rather than a shout. You take a step closer to the seam, and notice something unsettling about the emptiness everyone imagines before anything existed. Let's open this gently with our next big fact. The so-called vacuum is not a blank stage but a restless sea. In the quietest possible setup, where you would expect perfect stillness, tiny flickers appear and disappear as if the dark were breathing. You can picture it like the surface of a black ocean at night. No moon, no wind, yet ripples keep forming and dissolving with their own inexplicable rhythm. Later, we will call those ripples transient excitations, but for now, hold the image of a sea that refuses to be flat. And because every sea suggests a current, here comes another fact to anchor the image. Those flickers don't ask permission from time. They briefly borrow energy, create paired disturbances, and then cancel each other before the ledger can notice. You might think of them as soap bubbles that appear between your hands when you press them together underwater, sudden, shimmering, almost nothing, and yet their sparkle tells you the water was never truly still. Only after the metaphor has settled do we name them more precisely, virtual particles rising from quantum fluctuations. They are not solid marbles tumbling in space, they are momentary wrinkles in the rule book itself. Now let's let the surface metaphor thicken into something like terrain, because our next fact reveals a deeper texture. At the smallest scales, space is not smooth, it's foamy, jagged and wild, so wild that ordinary ideas like straight lines and stable distances begin to fray. Imagine shrinking yourself until a single second feels as long as a century, and a single grain of sand towers over you like a mountain. Down there, the horizon is constantly torn and mended, as if invisible fingers were kneading dough made of geometry. When physicists whisper about quantum foam, this is the landscape they're pointing to, a fabric with threads that won't sit still. You can already sense how such a fabric could become creative. So let a new fact open with a simple question. If the vacuum is energetic, why wouldn't it sometimes push beyond a mere flicker? Think of a hillside loaded with fresh snow. Most vibrations end as nothing, little slides that stop after a meter, but once in a while the buried layers align and an avalanche releases. In the same way, a fluctuation can be ordinary and cancel, or it can find a special path through the rules and grow into a domain that does not collapse. We'll soon speak of a field rolling down a potential toward a new state, but the image to keep is the sudden shift from harmless shuffle to unstoppable slide. There is a philosophical itch attached to this, so let's scratch it without losing the calm. If the deepest nothing available to our equations is already a kind of something dynamic, structured self-rumbling, does the word before even mean what you thought? You came here looking for a first rock, a first flame. Instead you find a surface whose most natural behavior is to make waves. The moral of the image isn't that we can pinpoint the exact ripple that became everything, it's that nothing behaves like an artist who can't help sketching. Creation, in such a world, isn't a miraculous exception, it's a tendency. Hold that thought, because our next fact begins with a whisper of responsibility. If a fluctuation can grow, it needs room. In ordinary space, size and time are strict partners, the canvas must stretch to accommodate the paint. But at tiny scales, the rules bend. The seed does not ask, where will I expand? The act of swelling generates its own arena, the way a soap bubble creates the interior air it encloses. Only later will we speak of a field whose energy acts like a pressure, driving expansion faster than light, without breaking the light speed rule for signals. For now, imagine the bubble rising from the sea, taking a piece of the sea with it, and making a world inside. This is where the metaphors must serve the mathematics, and not the other way around. So let another fact surface with clear edges. The background we've called a sea is defined not by particles but by fields, distributed, continuous entities that can hold energy even when they appear quiet. When those fields are in special, high-energy arrangements, they can drive space to stretch violently. You may hear it described as an unstable vacuum, deciding to relax into a calmer state, and the relaxation creates an enormous release. The key is that the vacuum isn't a cabinet of objects, it's a posture the fields adopt. Change the posture, change the world. If this rings like myth creation from the deep, remember, we are still being cautious. The scientist's caution is a kind of love. You owe reality the respect of asking, where would such a sea leave traces? Which leads to our next fact, softer but practical. The same foam that jitters when nothing else is happening could have planted the tiny differences that magnified later became galaxies. Unevenness in the sea becomes unevenness in the bubble. Unevenness in the bubble becomes unevenness in the sky. The breathtaking thought is that the largest structures, the filaments that bind clusters of galaxies into a cosmic web, may be fossils of those initial jitters. Noise amplified becomes pattern. There is humility here, and it matters as much as the physics. You might feel tempted to declare mystery solved, the vacuum did it, the foam did it, the bubbles did it, but each word you just used is a placeholder for equations we continue to refine and for measurements that could still surprise us. The right posture isn't triumph, it's readiness. Readiness to let the next observation nudge the image, to let the analogy break where it must, and to patch it with one that fits the data better. In this sense, the foam is not just a picture of space, it is a picture of knowledge itself, always wrinkling, always being smoothed and wrinkled again. You might also wonder about fairness. If the vacuum is so energetic, why isn't it raging around you now? Another fact arrives to answer, slipping in like a tide at night. Energy in the vacuum is not the same as energy in a flame. It is more like the baseline tension in a drumhead, present, decisive, but not noisy until struck the right way. In the early cosmos, conditions were set for that tension to act as a driving pressure. Today, in our cooled and expanded world, it shows up more subtly, giving the universe a slow outward push. The drum still hums, the song has changed. Every new image brings you back to the central cliff. If the sea is real and the foam is fertile, what turns ordinary flicker into decisive birth? The answer that modern cosmology pursues is not a single trigger, but a corridor of conditions. A field perched high on a slope, a path that lets it roll without dissipating too fast, a way for the released energy to turn into the particles and light we now count as everything. The profound part is that once the corridor opens, the process can sweep outward with astonishing speed, ironing away wrinkles while preserving just enough of them to plant the seeds of structure, smoothness and variety from the same mechanism, an elegant bargain. We are almost ready to take the step that the next section will make explicit. Before a universe can rebound, there must be something to rebound from. Before a universe can cycle, there must be a medium that remembers how to reset. The quantum sea you've been feeling your way through offers exactly that kind of memory, a capacity to hold energy, to release it, to settle, and to stir again, which is why the thought that comes next doesn't feel forced. It feels like the natural continuation of the same music. What if the sea doesn't simply make one bubble, but many again and again, in pulses, in eras, in breaths too long for us to time? Our next journey follows that music into a larger rhythm, the idea that the cosmos expands, settles, and then in ways that honor the same underlying rules, prepares the stage for another beginning. The foam becomes a heartbeat, the bubbles become cycles, and the quiet between them is not emptiness, but the pause that teaches you to hear the drum. You've just felt the vacuum tremble like a dark sea, which makes it easier to accept our next big fact. Some of the most compelling pictures of reality say the universe doesn't have a single arc but a rhythm. This is the heart of the cyclic idea. Creation isn't a one-time firework, it's a heartbeat that keeps returning, each thump separated by ages too vast to name. Rather than imagining a straight line from nothing to stars, you imagine a pulse, expansion, quieting, and a preparation for the next beginning. That subtle shift from line to loop changes how you listen to everything that follows. Lean closer, because the next fact enters almost as a correction to your mental picture. If there is a cycle, it is not a circle painted on paper, it's a living loop with stages, and one of those stages is contraction. You can think of it as a tide that does not simply rush in and keep going forever, but pauses, turns, and flows out. In this musical metaphor, the flowing out is contraction, space itself slowly drawing inward, distances shrinking, energy concentrating. After that inward phase, a bounce restores outward motion, and a fresh expansion begins. In the language you'll hear later, a prior cosmos approaches high density, avoids a fatal singular point, and rebounds into our own. For now, keep the image tide in, tide out, exhale, inhale, fall, then rise. This third insight begins softly, wrapped in memory rather than math, yet it deserves a seat at the same table. Long before anyone wrote down field equations, human cultures noticed the world's rhythms, seasons turning, eras rising and fading, stories of destruction followed by rebirth. Indian cosmology, for example, imagined vast cycles of creation and dissolution that unfold across incomprehensible spans, kalpas, as long as thought itself. You aren't borrowing these stories as evidence, you're letting them remind you that the mind has long been comfortable with beginnings that begin again. When modern physics entertains a cyclic cosmos, it doesn't validate myth, it rhymes with an ancient human intuition that time might breathe. Now we turn the lens to a sharper setting, because a scientific cycle needs more than poetry. Here is our next fact, a little unsettling in its implications. A bounce can act like a cleanser. When a contracting universe reaches extreme densities, certain models of quantum gravity suggest that information about earlier arrangements can be erased or blurred, the way chalk dust vanishes under a wet sponge. The equations name mechanisms, curvature terms that change sign at ultra-high densities, quantum discreteness that prevents a point-like collapse, but the image is enough. The blackboard is wiped, leaving only faint streaks. A fresh universe expands with a pristine look, carrying just traces of what came before. But this promise of cleansing runs straight into a stubborn, beautiful principle that insists on being heard. Our next fact begins here. Entropy, the measure of disorder, gives time its arrow and resists easy reset buttons. In any process where many pieces interact, disorder tends to increase. A cyclic cosmos must somehow keep entropy from growing without bound through each turn, or else every new cycle would be more chaotic than the last, eventually drowning structure in a heat-dead foam. The challenge is not cosmetic, it is structural. How, exactly, could a universe contract without collecting all its mess and hauling it through the bounce? This is where the science and philosophy braid into a single rope. On one hand, you're considering mechanisms. Perhaps during contraction, the universe dilutes its own mess into degrees of freedom that don't return in the same form. Perhaps the bounce couples to modes that carry away disorder like exhaust. On the other hand, you're asking what it means for a cosmos to remember. If the blackboard is wiped too clean, nothing that happens can speak of what came before. If it's not wiped at all, cycles cannot stay interesting. The sweet spot is a memory that is faint but real enough for continuity, not so much that the past crushes the present. That is the philosophical face of a technical demand. To steady the mind, bring back the tide. When a tide retreats, it doesn't take every shell with it. It leaves faint lines in the sand, curves of foam, scattered pebbles. Imagine a cosmic tide that behaves the same way. Contraction gathers, bounce washes, expansion redraws, some marks vanish, some marks survive as pale signatures. If that's true, you should be able to look at the present sky and find certain patterns that are too orderly to be accidents and too subtle to be noise, signs of a previous flow. Already, you feel the next section knocking. What could those signatures look like to our instruments? Before you answer, sink more firmly into how a cycle could run without entropic debt spiraling out of control. One approach treats dark energy, the gentle pressure that accelerates today's expansion, as a resource that can be staged across cycles. In some cyclic models, the late time acceleration stretches space so much that structures thin out, disorder becomes sparse, and the ingredients that would otherwise jam the next contraction are diluted beyond practical effect. The universe cleans the room by pulling it wide. In others, the bounce itself is not a single instant, but a brief era where interactions redistribute energy in ways that prevent a catastrophic pileup. Each avenue shares a goal: preserve the arrow locally while keeping the grand rhythm playable. You may worry that this sounds like engineering, and you'd be right. Cycles don't happen by magic. They require conditions that, if real, must be written into the deep rules. That's a feature, not a flaw. It forces the story back onto testable ground. If a cycle is possible, there should be calculations that predict how smooth the early universe should look, how tiny density ripples should be distributed, how gravitational waves should hum across the sky. Those predictions become the bait for our telescopes. The loop ceases to be a metaphor and becomes a hypothesis that can win or lose. There is another, quieter benefit to thinking cyclically, and it's not merely aesthetic. It loosens the tension that builds around uniqueness. A one-time beginning tempts you to ask, why these numbers, these constants, these starting conditions? A rhythm whispers, because rhythms select what survives. In a looping cosmos, parameters that produce stable, self-consistent expansion phases are the only ones that can cycle at all. Others crash or fade. Over time, immeasurable time, only rhythms that work keep playing. This is not a hand-waving answer to fine-tuning, but it's a reframing. Stability can be an outcome of repetition. Still, humility holds your sleeve. Not all roads to cycles are equal. Not all bounces are graceful. Some versions fail when confronted with precise measurements. Others struggle with internal consistency. That is the honest state of the art. The cyclic dream is viable only to the extent that it keeps clearing hurdles set by data, which invites a clean pivot. If faint signatures survive each loop, then the way to test the dream is to search the oldest light we can see for the sand lines left by another tide. So the rehook is simple and irresistible. We have a heartbeat, a contraction, a bounce that can cleanse but must bargain with entropy, and a promise that some memory remains. Where would you look for such memory? You would aim your instruments at the cold afterglow that still surrounds us, the cosmic background left from the earliest light, and you would comb it for patterns too stubborn to be random and too gentle to be new. The sky, if read carefully, might be a shoreline. In the next stretch we walk it, reading ripples of light for hints of a previous wave. You turn your attention to the sky's oldest message and open with our next big fact. The cosmic microwave background is not just faint afterglow, it is the oldest light you can observe directly, a snapshot of the universe when it was young and hot and just beginning to become transparent. Those photons have been traveling almost since the cosmos learned to let radiation go free. They carry the imprint of density ripples that would later grow into galaxies and clusters. When you map them across the whole sky, you see temperature variations so tiny they look like static, yet they encode an origin story. This is your baseline. The CMB is the fossil light of our beginning. Now, a new fact steps forward carefully because stakes are high. Within that fossil light, researchers have reported subtle anomalies that do not sit comfortably inside the simplest, smoothest model. The broad picture still fits. Random fluctuations with a nearly scale-free spectrum, but there are outliers that tug at curiosity. Large-scale alignments, slightly lopsided hemispheres, features nicknamed with playful gravity like the cold spot. None of these, alone, overthrows the prevailing picture. Taken together, they keep refusing to disappear into statistical noise. You could call them quirks, you could call them invitations. Either way, they urge you to look closer. Here is where the narrative edges toward the pre-Big Bang question, and another fact announces itself with restraint. Some teams have searched the CMB for concentric circles, patterns of unusually low or high variance arranged like ripples from an older splash. The logic is bold but simple. If a dramatic event occurred before our expansion, say a collision with another domain or a violent process in a previous cycle, its signal, stretched by expansion, might reach us as rings, not a photograph of the event, not a label, but a geometric whisper that something imprinted the plasma before light broke free. Circles, if real, would be the sky remembering. Before you leap, you need the counterweight, and the next fact provides it. The statistics of full sky maps are slippery. You look at one realization of the random process, the one universe you inhabit, and then judge how surprising its features are. That means anomalies can be both real and unsurprising. Real because they're truly there, unsurprising because a random field sprawled over a sphere will occasionally throw you a configuration that looks odd to human pattern hunters. Selection bias sneaks in easily. If you stare long enough, you will find shapes. The honest stance is to keep asking, how often would a model like ours produce this by chance? Even with the caution lamp on, the search continues, and here is your next fact stated plainly. If any pre-Big Bang imprint exists in the CMB, it must survive two brutal filters, cosmic inflation and the plasma's own smoothing. Inflation, if it happened, stretches space so dramatically that most prior memories are wiped or diluted. The hot, tightly coupled plasma then erases small-scale wrinkles before decoupling. Only large, coherent signatures could persist, and even those would be faint. That constraint is useful. It tells you which kinds of pre-Big Bang stories could ever speak through the noise. Theories that predict messy, small signatures are non-starters. This brings you to Data's philosophy lesson. You long for certainty, but your next fact is humility dressed as method. The current evidence for pre-Big Bang traces in the CMB is inconclusive. Some analyses report suggestive structures, others using different pipelines find the same maps perfectly consistent with chance. Two truths coexist. The CMB exquisitely matches the broad predictions of the standard model, and it houses curiosities not yet domesticated. The responsible thing is neither to declare a breakthrough, nor to deny intrigue. It is to build better instruments, test alternative statistics, and insist that reproducibility be the gatekeeper of wonder. The conversation is not only about circles and cold spots. Another fact quietly widens the lens. Polarization patterns in the CMB, how the ancient light is oriented, carry information complementary to temperature maps. Certain pre-bang scenarios would alter the spectrum of primordial gravitational waves, which in turn would leave a fingerprint in polarization called B modes. Detecting a precise spectrum could discriminate between ordinary inflation and more exotic prehistories. So the hunt has diversified, not just searching for geometry in temperature, but also listening for faint, twisting polarization that gravity's waves would weave into the sky. While the instruments refine, your philosophical half asks what it would mean to find a reliable pre-Big Bang signature. The next fact begins with a caution that protects you from over-promising. Even a confirmed anomaly would not instantly decode the before. It would narrow the space of possibilities. A ring pattern might favor a collision scenario. A specific gravitational wave spectrum could favor a bounce. But theories are families, and data points are ambassadors, not emperors. You would still need converging lines of evidence, perhaps from large-scale structure, perhaps from primordial element abundances, perhaps from laboratory probes of high-energy physics, to move from hint to history. Stand back a moment and consider the meta-signal. The CMB has already performed a miracle for you by letting precision cosmology exist at all. That itself is a fact worth savoring. A noisy map on the sky became a ruler for the cosmos. It measured curvature, set bounds on the content of matter and energy, and turned guesses into parameters with uncertainties. Against that achievement, the search for pre-Big Bang whispers is an act of gratitude as much as ambition. You are asking whether the same light that told you how our world grew might also, in its soft periphery, point to a world before. All of this leads to a necessary pivot, and you can feel the cliff's edge forming under your feet. Suppose the CMB never yields a definitive prehistory. Suppose the sky stays just ambiguous enough to tantalize. Then the next path must dive beneath the idea of before altogether. Another fact, ready to open, points the way. Some models do not merely push history earlier, they dissolve the question by treating time itself as emergent. If time began as a property that switched on when conditions were right, then asking what happened before is like asking what's north of the North Pole. Beautifully phrased, logically empty. And so the next section asks you to hold a paradox gently. How can there be a prior when time itself might be a child of the bang? Open this chapter with a quiet reversal that feels almost like a magic trick stated plainly. Our next big fact is that before the Big Bang may be a question without meaning, because time itself could be a feature that only turns on with our universe. In this view, the Big Bang isn't a firework in an existing clock, it's the moment the clock begins to tick. Asking what happened earlier becomes like asking what's outside the edge of a circle, when the circle is all there is. Elegant language, empty reference. The shock fades and a new calm arrives. Origins might be boundaries, not events. Let a companion insight step in gently, because it reframes what a moment is. Here comes another fact. Some approaches to quantum gravity treat time as emergent from correlations, not as an ingredient you sprinkle in at the start. In ordinary speech you say A causes B, then C, but in certain formalisms there's only a timeless state, and what you experience as flow is the way one part of the universe acts as a clock for another. Nothing moves with respect to an external watch. Subsystems coordinate, and that coordination is what you feel as duration. Time becomes relationship rather than substance. To make that less abstract, let this fact open with an image that serves the math. Imagine a vast score written for many instruments. There is no conductor measuring seconds. There is only harmony among parts. The violins change when the cellos change. The flute line breathes with the clarinet line. If you listen to one instrument alone, you swear you hear tempo, but the tempo is simply how that line relates to the rest. Likewise, in the timeless description, what you call now is a slice through a web of entangled relationships. The melody you experience as passing time is a path through that web. We can make the edge of time even smoother. Our next fact begins like a mathematician's kindness. If you allow time to take an imaginary value, rotating the axis the way you'd rotate a camera, certain singularities turn into rounded caps. There is no sharp first instant, there is a finite geometry without boundary, like the south pole of a sphere, where farther south doesn't exist, not because you hit a wall, but because the coordinate loses meaning. This trick isn't a shrug, it's a way to say that the equations prefer a universe that starts without a tear, and imaginary time is the stitching that prevents the rip. Of course, smoothing the edge raises a harder question that leads to another fact. If the deepest description is timeless, why does time feel so convincingly real? Why do memories sit behind you and possibilities ahead? One answer leans on entropy, the tendency for ordered arrangements to become disordered. When the universe is in a very special, low entropy configuration, there are many more states in its future than in its past, so typical histories will display a direction. Your brain writes memories because writing and storing them increases entropy. You don't remember the future because that would require patterns that reduce it. The arrow you feel is the counting of possibilities. Here comes a softer philosophical thread braided through the science. You are a creature who experiences duration from the inside. When models suggest that time is emergent or relational, they aren't gaslighting your experience, they are telling you there are two registers, the map and the journey. On the map, change is correlational structure. In the journey, change is heartbeat, breath and thought. The miracle is that these two registers agree where they must. The direction of entropy makes memory possible. Memory makes narrative possible. Narrative is how an organism predicts. The physics does not trivialize your sense of time, it explains why it works. Now, a different window opens onto the same room, and it's worth stating as a clear fact. The fundamental equation some approaches use to describe the entire universe looks eerily timeless. It says in essence that the total energy of the cosmos vanishes in the right accounting. So the wave function describing everything does not evolve in the usual way. To recover a flowing present, you identify pieces of that everything to play the role of clocks and compare all else to them. Flow is a derived feature. This isn't a parlor trick. It's a hint that time is not a universal ingredient, but a local strategy for keeping score. If the score is relational, then before can only mean in another relational domain, and that supplies the next fact. What you've been calling prior to the Big Bang could be a regime in which the variables that later behave like time had not yet distinguished themselves. Think of ice turning to liquid. The molecules are the same, but their freedom to slide defines a new experience of flow. Likewise, a pre-bang phase may have lacked the degrees of freedom that make clocks meaningful. With a change of state driven by geometry, fields, or quantum effects, those degrees of freedom emerged, and the world began to keep time. There is a psychological temptation to resist this picture, because it refuses a familiar narrative, so bring that hesitation into the light and meet it with a balancing fact. Not all models erase before, some retain a well-defined temporal variable that extends through a bounce or across a transition. Others define a direction in a larger arena, even if our clock starts later. The deeper lesson is not that time is an illusion or an absolute, it's that time may be layered. You can have coarse-grained time that survives across eras, fine-grained time that appears only after certain structures crystallize, and thermodynamic time that points the way probabilities point. Layered time softens the fight between exists and doesn't exist. This layered view carries a practical consequence you can test against your own life. Memory demands asymmetry, learning requires it, and anticipation feeds on it. If the arrow of time is bound to entropy's growth, then any theory of a beginning must explain why the initial conditions were so exceptionally ordered. That is the sting in the tail of every cosmology, emergent time stories included. A universe that starts with a remarkably smooth arrangement inherits a powerful arrow. If your origin story can also tell you why that arrangement was natural or inevitable, you've traded mystery for mechanism. If it can't, you've only moved the mystery to a prettier shelf. Let the next fact begin like a promise about scope. Treating time as emergent frees you to imagine structures adjacent to ours that do not share our clock. You don't need a universal metronome to have neighboring domains. You need rules that permit distinct relational webs. In one web, correlations support a robust arrow. In another, they don't. The idea of adjacency without shared time sounds paradoxical, but it's common in mathematics. Distinct solutions living in one broader space. Physics is simply asking whether nature plays the same game at the deepest level. All of this tilts your attention toward a natural rehook. If time is emergent, what else might be emergent with it? Here comes the last fact of this chapter, stepping in like a guide pointing at a door. The very space you move through, its three familiar directions, may also be an emergent facade, a coarse description of something richer underneath. If clocks arise from correlations, perhaps distances do too. Perhaps here and there are summaries of relationships on a deeper graph. That suggestion doesn't float alone. It meets you at the threshold of theories that add hidden directions, folded scales, and brane-like structures where collisions and transitions concede what we call a beginning. Which is why the next section doesn't feel like a departure so much as a continuation. If time can switch on, perhaps extra directions can switch open. If clocks emerge from correlations, perhaps entire universes emerge from the way higher dimensional sheets touch. You've learned to hold before gently. Now you'll learn to look sideways into dimensions you don't directly see, but that may have done the heaviest work in preparing the stage for everything you do. You've learned to hold time loosely, as something that might switch on rather than always be there. Let's open the door beside it with our next big fact. The most mathematically ambitious attempts to unify nature's forces invite more directions of space than the three you move through every day. In those frameworks, the universe is not a room with three walls. It is a corridor with hidden doors, some sealed so tightly you mistake the hallway for the whole building. The extra directions don't announce themselves because they are curled, folded, or stretched in ways that keep them beyond ordinary reach, like narrow stairwells that exist, yet are too tight for you to climb without special tools. Flow into a companion insight, softly marked as a new fact beginning now. If extra dimensions are real, they are not decorative. They can carry energy, host fields, and shape the behavior of gravity. A law that looks puzzling in 3 dimensions can seem natural when seen from a higher vantage, the way a shadow's strange outline makes sense when you turn toward the object casting it. What you call a particle could be the 3-dimensional slice of a higher dimensional vibration. What you call a force could be the way geometry in those hidden corridors pushes on our visible floor. You don't need to picture all of it, you only need to accept that sometimes the cleanest equations live in rooms you can't enter directly. A third piece of the puzzle steps forward, and we'll introduce it as our next fact with a steady hand. In several modern pictures, our entire observable cosmos could be a membrane, a brane floating in a higher dimensional bulk. You can imagine our brain as a sheet, flexible and wide, with all the familiar particles and forces trapped like painted patterns on its surface. Gravity alone has permission to leak, bending into the bulk and back, which is why it feels weaker than the other forces. It spreads its influence into places the others never visit. This view replaces the universe is everything with our universe is a surface, a bold but coherent move if you trust the mathematics that led you here. The fourth strand arrives with a little drama, because it whispers of beginnings in sideways directions. Here's the fact: if there are multiple branes drifting in the higher dimensional bulk, they can move relative to each other, and when they collide, The energy of that encounter can heat a brain enough to look from within like a firestorm of birth. The sequence is not nothing, then a bang, but two silent surfaces, then a touch that becomes light. The physics behind the picture speaks of potentials, separations, and tension. The image you hold is simple, sheets approaching, barely brushing, and suddenly a universe flares on the contact surface. Before the bang becomes a direction in which brains traveled, and the bang itself becomes an event of contact, not an emergence from a point. Allow yourself a pause for humility, then let another fact open in a lower voice. Our three-dimensional world may be only a slice through a structure with more depth, and that has practical consequences for what you can and cannot detect. If you live on a sheet, you cannot step off it, but you can spot how gravity misbehaves at short distances or high energies because it's stretching into the bulk. Experiments have chased tiny deviations from the inverse square law and looked for energy leaking in particle collisions like a magician's trick that fails to conserve what's on stage. So far, the data have narrowed the possibilities without closing the door. The hidden stairwells remain plausible even if unentered. Now let philosophy and physics braid again, because the next idea needs both. If sideways motion in invisible directions can light a universe, then before is a story about geometry, not emptiness. Time on our brain starts when contact injects energy. The prior is measured along a path we cannot walk, but the rules governing that path are the same rules that govern what we can see. This turns the notion of origin from a metaphysical cliff into a mechanical question. What set the brains in motion? What shaped the landscape through which they drift? And how often do such meetings occur? It also reframes solitude. Our cosmos might be one sheet among many, parallel, distant, perhaps differently painted with laws, but still neighbors in a wider room. That wider room suggests a gentle but profound test, and we can phrase it as the next fact with a clear promise. Hidden dimensions would not remain completely mute. They could influence what we call dark matter and dark energy, those dominant, invisible shares of the cosmic budget. Some proposals imagine dark matter as particles that live in the bulk or on a neighboring brane, but tug on our sheet via gravity, explaining why we feel their pull but cannot see their light. Others picture dark energy as the dynamic of brain separation, a tension in the higher dimensional fabric that acts on our surface like a gentle pressure pushing space to expand. In both stories, the darkness isn't a lack of substance, it's the presence of corridors we haven't walked. You can feel the narrative tightening as the implications converge. If gravity is the one force allowed to travel the bulk, it becomes your courier between worlds, and that courier might carry messages in the form of waves, ripples in space-time that could slide off our brain, propagate through the higher room, and return altered. That's not a prediction we can cash in casually, but it hints at signatures, deviations in gravitational wave spectra, tiny losses in energy that look like missing momentum, subtle fingerprints in how structures grow over cosmic time. You're not guessing wildly, you are learning to ask the sort of questions geometry itself compels. There is a human dimension to this that matters as much as any equation. You are tempted, always, by pictures that are easy to draw and comforting to hold. Spheres floating in a void, explosions within a pre-existing room. Hidden dimensions ask you to tolerate a different kind of simplicity. Equations that look cleaner in a space you can't visualize. That discomfort is a teacher. It reminds you that the mind's ease is not nature's obligation. If reality prefers a hall with narrow stairwells and thin sheets, your job is not to demand a wider stair, it is to learn how to read the scuff marks on the steps you can reach. Before we pivot, it helps to collect the facts you've gathered in this chapter. Extra dimensions can make the deep rules simpler. Our universe might be a brain suspended in a higher dimensional bulk. Collisions between brains can masquerade, from inside, as a big bang. Gravity's weakness might be the shadow of its freedom to roam, and dark matter or dark energy could be the fingerprints of those hidden corridors. Each fact leans on the others, and together they sketch a map where before lives sideways and origins are encounters, not eruptions. All that remains is to follow the map into the next valley, where the idea of collision stops being a static diagram and becomes a history with potential evidence. If a contact between brains heated our sheet into a newborn cosmos, then that cosmic touch may have left echoes, patterns in the oldest light, rhythms in the gravitational waves, textures in the distribution of galaxies that tell of the meeting. In other words, the birth cry of our universe would be a duet, not a solo. And that is the cliff you're standing on now. You've learned to look for beginnings in the folds, to expect light from a touch, to hear gravity as a messenger, The next step is natural. Listen for the echoes of colliding universes. If they exist, they are faint but patterned, like concentric ripples spreading far beyond where the stone sank. We turn to those ripples next, and we listen together. You've just stepped into a universe that may itself be a membrane floating in a higher dimensional hall. Now let's open this section with our next big fact. Some cosmologists suggest that what we call the Big Bang wasn't an isolated eruption at all. It was the echo of two branes colliding in that higher dimensional bulk. Imagine two enormous sheets drifting through an unseen expanse, silent and dark, until their touch sends shockwaves that from the inside look like fire, heat, and light. From within we call it a beginning. From outside it is simply an encounter, a moment of contact between surfaces that existed already. Once you let that picture settle, another fact comes alive. Such collisions wouldn't be perfectly quiet even after the flare. They could leave behind echoes in the form of gravitational waves, subtle ripples in space-time that preserve the memory of the clash. These waves, unlike light, can travel through matter almost undisturbed. If they were generated in colossal amounts at the moment of collision, traces of them could still be humming through the cosmos today, too faint for your ears, but not too faint for our detectors to one day confirm. That would mean the universe itself is ringing with the aftermath of an event older than our concept of time. Here's a third fact, stepping in with its own image. If brane collisions are real, they wouldn't always create neat single beginnings. Picture bubbles in a vast cosmic foam, each bubble representing a universe like ours. As these bubbles expand, sometimes they touch, overlap, and crash into one another. Each collision doesn't destroy the bubbles, it scars them like ripples etched into their surface. From the inside, such a scar might look like an anomaly in the cosmic microwave background, or an unusual pattern of density in the large-scale structure of galaxies. You're not staring at random imperfections, you're reading the graffiti of ancient encounters. The next fact is subtler but important. Our own Big Bang could have been one of those collisions, one chapter in a much larger drama. That would mean our universe is not the grand stage but a single scene, sparked by the brush of two branes in the vast hall of possibilities. From this view, the heat of the Big Bang wasn't the start of everything, but only the heating of our local patch. The wider play continues elsewhere, other branes drifting, colliding, and creating their own beginnings. In that sense, the word beginning becomes plural. Our start is simply one among many. To steady the scientific ground beneath the imagery, let's unfold another fact clearly. If such a collision truly occurred, it might leave measurable patterns that are different from those expected by standard inflationary theory. For example, the distribution of temperature ripples in the CMB could show ring-like structures, or the polarization patterns of ancient light could carry signals of anisotropy left from the impact. Researchers have already hunted for such circles in the sky, debating whether certain alignments hint at prior collisions. The evidence is not yet conclusive, but the very act of searching pushes physics forward. It transforms before from philosophy into hypothesis. A philosophical echo joins here, and it too is a fact of human experience. When you consider collisions of universes, you face the possibility that reality itself is crowded. You are not sitting in the only cosmos that ever existed, but one of many, each with its own history of encounters. Solitude dissolves. The night sky above you, instead of being an isolated dome, may be just the inside of one bubble among countless others, all drifting in a greater sea. That realization doesn't shrink your importance, it reframes it. To be aware of this possibility at all is already extraordinary. Another fact follows naturally. If collisions between universes have happened, they might happen again. A brane that once touched could, across incomprehensible stretches, touch again. To us inside, this could look like a sudden influx of energy, perhaps rewriting the rules of physics or ending the universe as we know it. That sounds frightening, but in truth, if such scales of reality are accurate, the time scales are so vast that again has no meaning within a human lifespan, or even within the lifespan of stars. It is a reminder that cosmic drama plays out in tempos far beyond our instincts. Let us balance fear with curiosity. Here's another fact. Some versions of this theory propose that each collision sets up the conditions for a new cycle of expansion and contraction, a cosmological bounce. If so, the Big Bang isn't the first or the last, it's one in a potentially endless sequence of impacts and rebirths. The universe doesn't end in cold stillness or fiery collapse, it resets again and again, each era seeding the next, each cycle layering memory into the very fabric of cosmic geometry. The story of reality becomes not a line, not even a circle, but a chain of encounters without a final link. And finally, a fact that serves as a hinge into what follows: if collisions can seed beginnings, then the scars they leave are crucial. Scientists are not content with elegant metaphors, they want fingerprints. The search for those fingerprints is already underway, in temperature maps, in polarization patterns, in gravitational wave backgrounds that may someday be recorded. The collision idea, bold as it is not forever beyond testing. It is a hypothesis waiting for data to confirm or refute it. That means before is no longer purely speculative. It has become something we can chase with instruments, with equations, with evidence. So you stand here at the edge of a universe scarred by possible impacts, and you ask, if encounters leave traces, how do they shape the order we see today? The answer pulls you straight into the next mystery, entropy itself. Because while collisions can reset and rebirth, the measure of disorder still lurks beneath every new beginning. And to follow that thread, you must now turn toward the riddle of why the cosmos began so ordered, and why disorder has been spreading ever since. That is where we go next. You've walked through echoes of colliding universes, each encounter leaving behind possible scars. Now the trail turns inward to something less visible but more commanding. Let's begin this section with our next big fact. The universe, at its very birth, emerged in a state of astonishing order. Against all odds, the early cosmos was low in entropy, a condition so precise that it has puzzled scientists for decades. Entropy is disorder, the number of ways a system can be arranged. And yet, despite the roaring heat of the Big Bang, the arrangement was not chaotic. It was balanced, delicate, as though the universe began its story with a clean desk, waiting for the clutter to arrive. Let that sink in before the next fact comes forward. The second law of thermodynamics, one of the most trusted rules in physics, insists that entropy must increase with time. That law gives you the arrow of time, the sense that the past is ordered and the future is messy. Coffee cools, eggs break, stars burn out, galaxies spread. But here lies the paradox. If entropy only rises, then why was it so low at the start? Why did the universe begin in a state that seems almost unnaturally tidy? This is not a small question. It's a crack at the very foundation of cosmology. A third fact enters, reshaping the paradox. Some scientists believe that the only way to explain the universe's uncanny order is to assume a pre-Big Bang mechanism that reset entropy. Imagine a cosmic reset button, pressed not once but as part of a larger cycle, washing away disorder and leaving behind a nearly smooth state from which expansion could begin. This connects directly to the bounce models you've heard of. If the cosmos contracts before rebounding, perhaps the contraction disperses complexity, spreading it so thin that the new expansion looks fresh. In this way, the second law remains unbroken. The reset is built into the rhythm. The fourth fact brings a sharper edge. Roger Penrose proposed a radical idea known as conformal cyclic cosmology. In his picture, the far future of our universe, when all matter has decayed, when black holes have evaporated, when only pure radiation remains, looks mathematically identical to a new beginning. In that geometry, the heat death of one cosmos is the seed of another. Entropy, which seems destined to climb without end, finds an escape through the transformation of time itself. The arrow is preserved, but the loop continues. In such a view, our low entropy beginning was simply the far future end of an earlier aeon. And here's a fifth fact, arriving with the gravity of philosophy and physics entwined. Entropy may not only explain the arrow of time, but also the very possibility of memory, identity, and story. If entropy had not been low at the beginning, there would be no contrast to make increase possible, no gradient to power processes, no reason for life or thought to emerge. Entropy's rise doesn't just tell you why ice melts, it tells you why you remember yesterday, but not tomorrow. It tells you why the past feels fixed, while the future feels open. Without the early universe's improbable tidiness, your very sense of continuity would not exist. But the paradox presses harder, and the next fact confronts it head-on. We don't yet know why the cosmos began in this special state. Inflation explains much, the smoothness, the uniformity, the structure, but it still requires the conditions that allow inflation to start. Why did the universe have the right arrangement to ignite such a process? Why wasn't it a chaotic froth from the first instant? Each theory pushes the question back, but doesn't yet erase it. The low entropy at the start is like a signature with no clear author. You might feel the frustration rising, but let's soften it with another fact. Entropy is not always a curse of disorder. In complex systems, rising entropy can drive creativity. Stars form because gas clouds collapse, releasing energy. Life evolves because energy flows from ordered sunlight into chaotic heat. Even in your brain, entropy shapes perception, guiding which signals stabilize into memories and which dissolve. The law that insists everything spreads also makes everything happen. In that sense, the puzzle of low entropy is not just a riddle of physics, it is the foundation of meaning itself. Let's place this in a wider frame with another fact. Some scientists suspect that entropy's paradox might be an illusion of perspective. Perhaps the universe as a whole has no preferred direction, but from within you experience one because of how subsystems like ours trace correlations. What you call low entropy could be the part of the system you can see, selected because only such a patch can give rise to beings who ask these questions. This is a controversial stance, the anthropic principle applied to time, but it remains on the table. Maybe our ordered beginning is less about fate and more about selection bias. Still, caution keeps you steady. Another fact deserves mention. Even the anthropic idea doesn't fully answer the problem. Physics seeks a mechanism, not just an explanation of why observers find themselves in rare conditions. The honest truth is that entropy's origin is still open, one of the deepest mysteries left unsolved. And in that openness, science and philosophy both thrive. The unanswered question keeps cosmology alive as a discipline. It is the unsanded edge of our story. So gather the facts you've carried through this chapter. The early universe's improbable order, the arrow of time tied to entropy's rise, the possibility of cosmic resets, Penrose's conformal cycles, and the role entropy plays in memory and meaning. Each fact interlocks, shaping the paradox without resolving it fully. And as you hold them together, the cliff edge forms again. If entropy gives you an arrow, what planted the seeds that grew along its path? If disorder's rise shapes your story, what provided the first unevenness for the story to build upon? That is where the next section carries you, into the quantum seeds of reality itself, the tiny fluctuations that bloomed into galaxies, and perhaps clues of what stirred before the bang. You've stood at the puzzle of entropy, where order at the beginning felt impossibly precise. Now the story shifts into the delicate marks left upon that order. Let's begin this section with our next big fact. The vast galaxies you see today, spiral arms glittering with stars, clusters bound together in cosmic webs, trace their origin to tiny quantum fluctuations. These were minute differences in density, no bigger than whispers in a storm, yet they became the scaffolding upon which all structure grew. Without those fluctuations, the universe would have remained smooth, like a desert with no dunes, a canvas with no paint. The next fact flows from this. These primordial ripples existed even before cosmic inflation stretched space. In fact, inflation magnified them. Imagine an artist's pencil marks on paper, almost invisible until someone takes the sheet and expands it into a mural. What were once subatomic jitters became macroscopic features. Inflation didn't just blow up the cosmos, it blew up the tiny differences in density, freezing them in place so that billions of years later, gravity could sculpt them into galaxies. The fingerprints of those ripples are still visible today in the cosmic microwave background, a record of the first brushstrokes. A third fact arrives with a touch of paradox. Those fluctuations were random, yet they created order. Quantum uncertainty means you cannot know both position and momentum perfectly, so space itself trembles with unavoidable noise. But when inflation magnifies that noise, the randomness becomes pattern, like static on a radio that somehow arranges itself into music. The universe turned quantum randomness into cosmic architecture. This is not metaphorical flourish, it is literal. The balance between uncertainty and expansion gave rise to everything from the Milky Way to the ground beneath your feet. Here comes a fourth fact, more technical, but just as awe-inspiring. Experiments on Earth have tried to simulate aspects of this quantum foam in the lab. Physicists create ultra-cold atomic systems where fluctuations can grow and spread, imitating the dynamics of early universe fields. These tabletop universes don't reproduce the cosmos in scale, but they mirror its rules. In their patterns, scientists glimpse how random seeds can cascade into large-scale structure. The laboratory becomes a tiny echo of the pre-Big Bang tremors, allowing human hands to reenact the dance of creation. And now a fifth fact, one that closes the circle with the riddle of before. Some of those fluctuations might not be native to our universe at all. Certain theories suggest they could be echoes, imprints from a prior cosmic state carried across the seam of the Big Bang. If a previous universe existed and contracted, the jitter in its quantum fields might have bled into our beginning, leaving behind seeds that inflation then stretched. In that case, the galaxies lighting our sky today would be fossils of a reality older than our own, whispers that survived the collapse and bloom of entire universes. Pause here, because the philosophical reflection rises naturally. When you look up at the stars, you are not just seeing glowing gas or nuclear furnaces. You may be seeing the physical embodiment of uncertainty itself. Galaxies exist because reality cannot be perfectly smooth, because randomness is baked into the fabric of existence. Without that imperfection, no story would unfold, no planets, no life, no thought. The flaw is the feature. What feels like chaos at the smallest scale becomes meaning at the largest. This realization carries another quiet fact. The structure of the universe is a map of its memory. Every cluster of galaxies, every filament stretching across millions of light years, is a fossilized amplification of quantum tremors. The cosmos is not only expanding, it is remembering. And this memory is written not in words or symbols, but in the very placement of matter across space. To gaze into the sky is to read a book written in probabilities, each page the result of noise given time to grow into architecture. But memory also raises attention, and here another fact insists on being spoken. We can only observe part of this memory. Inflation's stretching not only magnified fluctuations, it also pushed many of them beyond our cosmic horizon. Those seeds are forever out of reach, lying beyond the limits of light's travel since the beginning. That means our view of the quantum ancestry of reality is partial, like trying to read a book with half the pages glued shut. Still, what remains is enough to tell the broad strokes of the story. Randomness became the pattern, and pattern became us. One more fact sharpens the scientific edge. Satellites like COBE, WMAP and Planck have confirmed that the statistical distribution of those primordial fluctuations matches almost perfectly the predictions of inflationary models. This isn't a vague metaphor, it is precise data, numbers written into the fabric of the microwave background. Slight deviations exist, and they may one day hint at deeper truths, but the match itself is extraordinary. It tells us that the seeds of everything were indeed quantum in origin. That's as close as science has ever come to proving that uncertainty itself gave birth to the stars. Let the closing lines of this section bend back toward the philosophical, readying the cliff for what follows. The universe began with low entropy, yet seeded with small imperfections. Those imperfections grew into beauty, randomness into galaxies, noise into memory. If such fragile marks could survive inflation and become the cosmos we know, then perhaps they also carry clues not just of our beginning but of what preceded it, which leads to the natural next step. If the seeds are quantum, the soil in which they grew is inflation, and inflation, with its explosive expansion, carries paradoxes of its own. So now we turn there to the grand mystery of cosmic inflation, its triumphs, its puzzles, and what it hides about the era before. You've seen how tiny quantum fluctuations became the seeds of galaxies. But those seeds would never have blossomed if not for something stranger still. Let's begin this chapter with our next big fact. The early universe experienced a period of inflation, an expansion so rapid that space itself stretched faster than the speed of light. This does not violate relativity, because nothing was moving through space faster than light. Instead, the fabric of space was expanding, carrying everything with it. In less than a heartbeat, the universe grew from subatomic size to something vast enough to appear smooth and uniform. Inflation wasn't just growth, it was a rewriting of scale itself. Here's another fact, slipping in with precision. Inflation solves three major puzzles that once haunted cosmology. The horizon problem. Why is the cosmic microwave background so uniform across regions that could never have communicated? The flatness problem. Why is the geometry of the universe so close to perfectly Euclidean? And the monopole problem. Why don't we see heavy relic particles predicted by grand unified theories? Inflation acts like a cosmic eraser, stretching irregularities and relics beyond our reach, leaving behind the smoothness we measure today. It is a solution so elegant that it reshaped cosmology from the 1980s onward. But elegance conceals new riddles, and the third fact rises from those shadows. We still don't know what triggered inflation. The theory requires a field called the infloton that carried enormous potential energy, driving space to expand. Yet the identity of this field remains a mystery. Was it a new kind of particle? Was it a property of space-time itself? Or was it the remnant of physics operating at scales far beyond what we can test? Without knowing the engine, inflation is more a map of effects than a description of causes. You can see the footprints, but the walker remains unseen. Now, a fourth fact steps forward, one that makes inflation stranger still. In many models, inflation is not a one-time event. It is eternal. As some patches of space stop inflating and form bubble universes like ours, other regions continue to inflate endlessly. The result is a fractal-like multiverse, with infinite domains, each expanding, each carrying its own version of physics. From this perspective, our observable universe is just one bubble that happened to stop inflating when and how it did. The cosmic acceleration you see today could even be a faint echo of inflation, still tugging at the edges of the larger whole. Let's deepen the paradox with another fact. If inflation is eternal, then before the Big Bang might not be a unique state but an ongoing process, a perpetual field of expansion that has no beginning and no end. In that picture, the bang isn't the start of everything, it is just the local end of inflation, when energy was released into radiation and matter. In other patches, other bangs are happening even now. The ultimate origin is not an instant, but a field that never stops, a process that eternally births universes. Time itself may stretch endlessly backward in that inflating sea. This thought invites a pause for reflection, because philosophy joins physics here. You crave beginnings because stories need first chapters, but inflation whispers that reality may not have one. Instead, it may be an infinite story with countless entry points, each one a bang to the creatures living inside. To ask what came before might be like asking where a circle starts. The answer depends on where you choose to place your finger. Even so, science demands something more concrete, and so comes another fact. We can look for observational evidence of inflation in the cosmos we inhabit. Tiny patterns in the CMB's temperature fluctuations, the statistical distribution of galaxies, and above all the search for primordial gravitational waves, all act as tests. If inflation occurred, those waves would have been stirred like ripples in space itself, leaving behind a faint spiral imprint in the polarization of ancient light. Telescopes have already searched for this signal. Some claims have risen and fallen, but the pursuit continues. The promise is clear. If detected, such waves would confirm inflation's fingerprint directly. Let's add another fact that grounds the conversation. The shape of the primordial fluctuation spectrum, merely scale invariant with slight deviations, fits inflationary predictions with remarkable accuracy. This is not philosophy, it is data. The Planck satellite mapped the sky with such precision that the small tilt in the spectrum predicted by inflation was confirmed. That is why inflation remains the dominant paradigm. It has predicted features that later measurements revealed. Yet, as strong as it is, the mystery of the inflation field remains unsolved. It is like having a crime scene, the tracks and the evidence perfectly matching, but the culprit never appearing. And here's a fact that feels more unsettling. Inflation may not be the only explanation. Competing models, such as bouncing cosmologies or emergent scenarios, can also account for some of the same data. Each carries its own challenges, but their existence proves that cosmology has not yet settled the matter. We have compelling evidence for something inflation-like, but whether inflation itself is the correct story or just one chapter in a larger book remains to be proven. This uncertainty is not weakness, it is the strength of science. A theory must remain open to replacement when better evidence comes. So collect the truths from this section. Inflation stretched space faster than light. It solved major cosmological problems. Its engine, the inflation, remains unknown. It may be eternal, spawning endless bubble universes, and its fingerprints are written in the structure of the cosmos, though rival models keep the door of doubt ajar. Now, let the rehook settle into place. If inflation may be eternal, if bubbles of universes bloom within its sea, then our cosmos is not alone. And that brings us to the next idea, perhaps the most daring of all. What if there are not just other patches of space inflating beyond our view, but entire universes, each with their own laws, existing side by side in a vast multiverse? That is where the story carries you next. The last chapter left you with inflation blooming endlessly, spilling bubbles of space into a sea without borders. It's the perfect doorway into our next big fact. The multiverse hypothesis suggests that our universe is just one bubble among countless others. Each bubble may carry different physical laws, different constants, even different numbers of dimensions. From the inside, every bubble feels complete, like the whole of reality. From the outside, if such a vantage were possible, they are simply parts of a greater quilt, stitched together by the same underlying fabric. Now comes another fact, equally astonishing. Some of these universes could have existed before ours in ways that stretch your sense of sequence. If inflation is eternal, then new universes form without end, but also without beginning. The multiverse has no origin point, it simply always is, birthing new patches forever. In that scenario, what you call the beginning is not a unique event, but just the moment our bubble detached from the inflating sea. The bang is a local birth, not a universal one. The next fact enters like a subtle echo of quantum mechanics. Every decision, every uncertainty may spawn branching realities. In the many worlds interpretation of quantum theory, every possible outcome exists somewhere, not as abstraction, but as parallel branches of reality. If you marry that idea to cosmology, then the multiverse is not only bubbles in space, but branches in possibility. A universe where the electron spun left, another where it spun right. A universe where inflation ended in one way, another where it ended differently. Suddenly, the multiverse is both cosmic and quantum, stretching in all directions of possibility. Here's a fact that anchors the thought in evidence. The multiverse is not pure fantasy. Its strongest argument comes from the fine-tuning of constants in our own universe. Physical laws are exquisitely balanced to allow stars, chemistry, and life. Change the strength of gravity slightly, and galaxies never form. Alter the charge of the electron, and atoms collapse or never bind. In a single universe picture, this looks like an impossible coincidence. In a multiverse, it is natural. With countless variations, some bubbles inevitably have the right conditions. We live in one, not because it was destined, but because only such bubbles can host observers like us. A fifth fact sharpens this with humility. If the multiverse exists, then much of it will remain forever beyond observation. Other bubbles may be separated by regions of space still inflating, faster than light can cross. Even if they lie nearby in the larger structure, no signal could bridge the gap. That doesn't make the hypothesis useless. It means its testability requires creativity. Scientists search for indirect hints, such as patterns in the CMB that might result from bubble collisions, or mathematical necessities arising from theories like string theory. The multiverse is not yet proven, but it is more than imagination. It is an inference from the models that already explain what we see. Let's pause for philosophy, because the idea itself reshapes meaning. If our cosmos is one bubble among many, then the question "why are we here" shifts in tone. The answer may not be cosmic intention, but statistical inevitability. Somewhere, conditions had to be right. This is not to trivialize existence, it is to realize that rarity doesn't always imply design. Sometimes rarity is simply the product of vastness. In an endless ocean, even improbable waves will form. Another fact follows from that vastness. Some universes in the multiverse might operate under laws so alien that life, stars, or matter as we know it cannot exist. Imagine a cosmos where gravity is repulsive, where time flows in multiple directions, where no stable atoms form. These universes would flare into being and vanish, or persist in states we can barely describe. Their existence would never be known from within ours, but their possibility expands your imagination of what is. The multiverse makes even the wildest physics seem tame, because everything permitted by the larger rules must eventually occur somewhere. A quieter fact joins in, bridging physics and philosophy. If the multiverse is real, it challenges the uniqueness of human knowledge. Science has always aimed to describe the universe as a singular whole, but if the universe is only one bubble, then science must accept its limits. Our laws describe our bubble, not necessarily the totality. This does not weaken science, it humbles it. Just as Newton's laws describe a domain but not all reality, our cosmological laws may be local, not universal. The multiverse reframes our theories as chapters, not the entire book. And then comes a fact with teeth. The multiverse, though vast beyond vision, may leave subtle fingerprints in our observable sky. A collision with another bubble, if it happened during inflation, could leave a circular mark in the CMB, or a distortion in the distribution of galaxies. Gravitational waves, too, might carry imprints from interactions with other domains. Detecting such signs is immensely difficult, but not impossible. If found, they would transform the multiverse from speculation into observation. Scientists continue to refine their instruments, scanning the sky for these faint scars. Gather the truths of this chapter. Our universe may be one bubble in an infinite sea. Other universes may have existed before ours. Quantum mechanics hints at branches of reality. Fine-tuning suggests a selection effect across many worlds, and though distant bubbles may be inaccessible, their collisions could still leave marks in our own. Each fact draws you deeper into the idea that everything is larger than any one cosmos. And so the cliff edge appears again. If entire universes can be born, live, and vanish within the multiverse, then what mechanism could link them? Is there a bridge, a doorway, a connection between one cosmos and another? The next step takes you into the darkest places of physics, where gravity collapses matter into points of no return. Black holes, the most terrifying abysses of our universe, may also be gateways to others. That is the secret waiting in the next chapter. You've wandered through the idea of the multiverse, where countless universes may bloom like bubbles in an endless sea. Now the trail narrows towards something more intimate, something already present in our cosmos. Let's begin this chapter with our next big fact. Black holes, long feared as dead ends of physics, may also act as gateways. The same equations that describe collapse and horizons suggest that beyond the veil, space-time may continue, not end. Instead of being a tomb, a black hole could be the womb of another universe, its singularity the echo of a Big Bang happening elsewhere. Let the second fact step in, because the rules inside a black hole defy what you know. When matter collapses past the event horizon, the structure of space-time warps so severely that ordinary cause and effect collapse with it. Your familiar sequence of past, present, and future no longer applies. The density rises toward infinity, and the laws of general relativity, so successful everywhere else, tear apart. It is here, in this breakdown, that the possibility of birth lurks. If relativity alone cannot describe the interior, perhaps the true laws at quantum scales allow something new to emerge. Now comes a third fact, offering a surprising mirror. The equations of Einstein admit solutions not just for black holes, but also for their opposite, white holes. A white hole is a theoretical region where matter can only escape, never enter. The reverse of a black hole's prison. If such entities exist, they could be linked, the collapse in one domain, the eruption in another. What you call a singularity in a black hole might, from the other side, look like a bang. This symmetry suggests that our own Big Bang could have been the interior of a black hole formed in a parent universe. A fourth fact unfolds with the weight of imagination, but also with grounding in physics. Some researchers have proposed that every black hole might seed a new universe. In this view, the collapse doesn't destroy matter but compresses it through a throat of space-time, which then expands elsewhere. Each black hole becomes a cosmic womb, budding off a fresh cosmos. Our universe, then, could be the child of another, born in the heart of a black hole that once existed in a grander cosmos. This transforms black holes from endings into branching points in an infinite cosmic genealogy. Now let the next fact open as a bridge to observation. Stephen Hawking showed that black holes are not completely black. They emit faint radiation, Hawking radiation, that allows them to evaporate over immense timescales. This fact raises a tantalizing possibility. The evaporation could serve as the handshake between one cosmos and another, the gradual transfer of information across the horizon. Instead of being destroyed, information might be encoded, transformed, and carried into a newborn domain. If so, black holes preserve continuity across universes, linking past and future in ways we barely comprehend. A sixth fact slips in here, reinforcing the depth of the puzzle, the information paradox. One of the most famous unresolved problems in physics is tied to this very question. When matter falls into a black hole, is its information truly lost? Quantum theory forbids such loss, but relativity seems to demand it. The resolution to this paradox may reveal whether black holes are bridges. If information survives by traveling into another universe, then the paradox dissolves not through destruction, but through expansion. The mystery of black holes becomes the mystery of beginnings. Pause for a moment, because philosophy must walk beside the equations. If every black hole is a seed, then reality itself is fecund, always birthing new worlds from collapse. Death and creation cease to be opposites. They become phases of the same cycle. Stars collapse, black holes form, and with them the possibility of entire universes. The metaphor becomes almost biological. Universes reproduce. If true, the cosmos is not a solitary narrative, but an evolutionary tree, branching endlessly through generations. This thought leads to another fact, one tied to Lee Smolin's idea of cosmological natural selection. He proposed that universes born inside black holes might inherit slightly altered physical constants. Those that produce more black holes will therefore spawn more offspring universes. Over countless generations, constants would evolve toward values that maximize black hole production. In this bold picture, our universe's finely tuned laws are not a coincidence. They are the result of cosmic evolution. We exist in a universe optimized for reproduction, and life is a fortunate byproduct of that optimization. Let another fact emerge, more cautious but just as vital. None of this has yet been confirmed. Black hole cosmogenesis remains speculative, balanced between bold imagination and mathematical possibility, but speculation is not aimless, it directs observation. Physicists test these ideas by probing gravitational waves from black hole mergers, by studying Hawking radiation in analog systems on Earth, by searching for subtle clues in cosmic structure. Even if black holes are not literal gateways, their study continues to sharpen our understanding of space-time, quantum theory, and the fragile boundary between collapse and creation. Here is the final fact of this chapter, one that brings you back to where it all began. The Big Bang itself bears the same mathematical signature as a singularity. It is a place where relativity breaks, where density soars, where familiar laws collapse. If black holes and bangs share this structure, then the possibility that one can transform into the other is not fantasy but a question written into the equations. To ask what was before the Big Bang may be the same as asking what lies inside the heart of a black hole. The answers may be identical. So collect what you've gathered. Black holes may continue beyond their horizons. White holes provide a mirror image. Each black hole could seed a universe. Hawking radiation might carry information across domains, and the very paradoxes of information hint at bridges instead of walls. Each fact transforms the image of a black hole from an end into a doorway. And now the cliff emerges again. If black holes can birth new universes, then mathematics itself is the midwife. The very structure of numbers and infinities may contain hints of what exists before and beyond, which is why the next step takes you not into an object of matter, but into the abstraction that frames all matter, the mathematics that reaches beyond infinity, and the clues it whispers about what preceded the bang. You've just crossed the dark horizon of black holes, discovering that they might not be tombs but gateways. Now the path turns even more abstract, into the silent realm that underlies every equation. Let's begin this chapter with our next big fact. Infinity is not a poetic exaggeration, it is a result that naturally appears in cosmological equations. When you trace general relativity back to the singularity of the Big Bang, or when you let densities climb without bound inside a black hole, the math does not stop at large numbers, it goes straight to infinity, a signal that our current theories have reached their limit. Infinity is the red flag of physics, telling us that there must be a deeper layer beneath. From that starting point comes another fact. Some of these infinities are not just breakdowns but possible hints of pre-universe structures. In quantum field theory, calculations often blow up to infinite values, but renormalization, the careful subtraction of self-references, restores finite results. The persistence of infinities, though, suggests that space and time may not be continuous. Instead, they might be quantized, granular, like pixels on a screen. If so, the apparent infinity at the Big Bang could be an illusion created by trying to measure with the wrong ruler. Beneath the illusion lies structure, perhaps a lattice or network that predates the bang. Now, a third fact steps in with a twist. Kurt Gödel, famed for his incompleteness theorems, discovered exact solutions to Einstein's equations where the universe rotates. In these rotating universes, time loops back on itself, allowing for closed time-like curves. Such solutions are not our reality, but they reveal something profound. The mathematics of space-time admits worlds where before and after intertwine, where cause and effect become circular. Gödel's mathematics whispers that the question of what came before may be answerable only in geometries stranger than we can picture, worlds where time has no edge at all. The next fact opens from the realm of negative numbers, a place where intuition struggles but equations thrive. In cosmology, negative energy states are not nonsense. They are tools that balance the equations of expansion. Vacuum energy, dark energy, and the very act of inflation depend on such negative values. These states allow the universe to be born from nothing without violating conservation. Positive energy of matter and radiation is offset by the negative energy of gravity, yielding a total energy close to zero. In that sense, the cosmos may have required no external input. The math itself allows for self-creation. What we call nothing is balanced bookkeeping, and that balance is a fact written in the equations. Here comes a fifth fact, softer in tone but vast in implication. Infinity may not be a single entity, but a landscape of different sizes and kinds. George Cantor showed that some infinities are larger than others, that the infinity of real numbers dwarfs the infinity of counting numbers. When cosmologists confront the idea of an infinite multiverse, or eternal inflation producing endless bubbles, they face the problem of comparing infinities. Which infinities count more? Which can be measured? The challenge is not philosophical wordplay, it is a mathematical necessity. Without a way to tame infinities, predictions lose meaning. Infinity, in this sense, is not just a breakdown, it is a structure waiting to be organized. Pause here and let philosophy enter. If infinity appears naturally in our deepest equations, it may be more than a mistake. Perhaps it is a window into the pre-bang realm, a place where the boundaries we know dissolve into something limitless. Humans recoil from infinity because it breaks narrative. We want beginnings, middles, and ends, but reality may not. A universe that existed before the Big Bang may not be a finite object to be explained, but an infinite one, of which our cosmos is a single finite part. What feels like paradox is simply the scale of truth. This thought flows into another fact. Some cosmologists suggest that infinity is not out there, but built into the geometry of space-time itself. In a flat, infinite universe, the volume extends forever, and so does the potential for matter and energy. This suggests not only endless stars and galaxies, but endless repetitions of configurations. Somewhere in this infinite expanse, there may be another version of you, sitting under another night sky, asking the same questions. This isn't mystical speculation, it's a straightforward consequence of infinity applied to physics. The idea that before the Big Bang could be infinite space is therefore not impossible, but consistent. Yet another fact emerges, tying infinity back to origins. Mathematical models of a zero-energy universe suggest that a cosmos can arise spontaneously because total energy balances to nothing. Infinity here is not size but potential, an unbounded range of fluctuations, one of which becomes stable and expands. The bang in this picture is simply one realization out of infinitely many attempts. The fact that we are here is not surprising. In an infinite backdrop, even the rarest events will occur somewhere. Infinity doesn't just frighten, it guarantees creation. Finally, let's land with a fact that transitions smoothly to what follows. Infinity is not only a concept of numbers, but also a link between science and myth. Ancient traditions often spoke of eternal cycles, endless time, or boundless space. Today, mathematics gives infinity precise form, embedding it into the equations that describe the cosmos. The strange truth is that myth and math converge here, both pointing toward a reality that has no ultimate boundary. This resonance between human imagination and mathematical structure is more than coincidence. It may be a clue that the universe's deepest truths live at the border of logic and wonder. So gather what you've uncovered. Infinities arise in equations, hinting at deeper pre-bang structures. Gödel's solutions suggest time could loop. Negative energies balance creation. Cantor's infinities challenge prediction, and the zero-energy idea reveals how a universe can bloom from nothing. Each fact sharpens the possibility that mathematics itself is the key to understanding what came before. And now the cliff appears again. If numbers can speak of infinities and equations hint at structures beyond time, perhaps science is not the only voice here. Myths, long dismissed as fables, may hold surprising parallels to the questions of physics, which is why the next step is not to dive deeper into equations, but to glance sideways into the stories humans told long before telescopes, stories that might whisper what was before the beginning. You've just walked through the vast halls of infinity, where mathematics itself becomes a guide to what might have existed before the bang. Now we turn to a different kind of memory, older than science, carved into the imaginations of cultures across the earth. Let's begin this chapter with our next big fact. Hindu cosmology described the universe as cyclic, born and dissolved in endless ages called kalpas. Each cycle lasted billions of years by their reckoning, echoing expansion and contraction long before modern physics gave us the language of bounces and cycles. In those ancient texts, the cosmos has no single beginning or end. It breathes eternally, like a cosmic chest rising and falling. That vision resonates uncannily with what scientists now explore mathematically, flow gently into the next fact. Norse mythology speaks of Ginnungagap, the yawning void that existed before creation. This gap was not empty in the modern sense, but a charged nothingness between realms of fire and ice. From their meeting, the first forms emerged, shaping the world. To a physicist, this feels strangely like the quantum vacuum, not truly empty but pregnant with potential, where opposites can collide to spark existence. Myths didn't use the vocabulary of fields or particles, but they sensed the paradox. Creation begins not from fullness, but from a void charged with possibility. Here's a third fact. Unfolding from the ancient Americas, Mayan cosmology described multiple ages of the world, each destroyed and remade. In their vision, universes are fragile, ending in fire, flood, or transformation, only to give way to a new creation. The resonance with multiverse theories is striking. Where modern physics imagines endless bubbles or cycles, Mayan myth saw repeated births and deaths. Both insist that what we live in is not singular or final. The cosmos has chapters, not a lone page. The fourth fact in this chapter ties all these echoes together. Many ancient myths align eerily with cyclic or pre-Big Bang concepts, not because they were proto-scientific theories, but because the human mind has always grappled with beginnings. It resists the idea of absolute nothingness. It senses that time may loop, that voids are fertile, that destruction is followed by rebirth. Science, with its telescopes and equations, now stands where myth once stood, with stories about cycles, voids, and rebirths. The overlap does not prove the myths, but it reveals that imagination and observation often converge on similar shapes when confronted with the infinite. Pause now, because philosophy enters through the same door. What does it mean that myths from across the globe imagine cycles, voids, or multiple creations? Perhaps it reflects a deep cognitive bias that humans cannot bear the thought of a beginning without a background. Or perhaps it reflects something more, a resonance between the way reality works and the way imagination senses it. Just as myths once intuited atoms or worlds beyond ours, they may also have intuited that existence is layered, never absolute, always emerging from something older. Let another fact emerge, softer but still compelling. Modern cosmology sometimes borrows mythic metaphors to explain itself. We call it the cosmic egg, the primordial fire, the big bounce. These words remind us that even as we wield equations, we lean on images older than science. Myth is not discarded, it is recycled as language, a bridge between the incomprehensible and the familiar. The continuity between ancient myth and modern physics is not evidence of truth, but evidence of necessity. To talk about what came before, you need metaphors, and metaphors have always been the work of myth. At this point, the facts you've gathered in this chapter can be seen as mirrors. Hindu cycles, Norse void, Mayan destructions, all whispering of rebirth, void, and multiplicity. Each myth becomes a reflection of the same questions scientists now formalize, and that brings you to the cliff again. If stories from long ago converge with models of today, perhaps the next step is not to look at imagination, but to return to physics itself, because physics holds something myths could not, the precision of symmetry. The laws of nature are written in balances, mirrorings, and breakings of those mirrors, and those symmetries, unfinished or broken, may carry the clearest clues of all about what existed before the bang. You've just listened to the whispers of myth, where cycles, voids, and rebirths painted ancient skies with meaning. Now the lens sharpens back to physics, and here is our next big fact. The laws of nature are built on symmetry. At the deepest levels, forces and particles often look interchangeable, until broken symmetries create the diversity we observe. Think of a perfectly round drop of water freezing into a snowflake. The symmetry is hidden, fractured, and out of the break new patterns emerge. In the early universe, and perhaps even before the bang, the rules of symmetry were more pristine than what we see now. The second fact follows like the echo of a mirror. At extreme energies, forces that today appear distinct, electromagnetism, the weak force, and even the strong force may unify into one. This idea of grand unification suggests that before the universe cooled, the laws of nature were not fractured but seamless. Only as temperatures fell did the forces split apart, like light separating through a prism. That means the deeper you peer into the past, the closer you approach a state where symmetry reigned unbroken. And if you go past the bang, perhaps that state existed before, waiting in silence to differentiate again. Here comes a third fact, stepping softly but firmly, the electroweak force, which unites electromagnetism and the weak nuclear force, is evidence that such unifications are real. Above certain energies, these two distinct interactions behave as one. That is not speculation. It is tested physics, confirmed in particle accelerators. The fact that we see this unification in our own experiments strengthens the idea that even higher symmetries may exist at scales unreachable so far. In those hidden symmetries may lie the blueprint of a universe before the bang. The fourth fact appears like a pattern in glass. Supersymmetry, though still unconfirmed, is one such candidate. It suggests that every known particle has a heavier partner, a mirror sibling we have yet to see. If true, supersymmetry would solve problems about dark matter and unify interactions more smoothly. But more than that, it would hint at a deeper order from which our visible world emerged. Even if experiments have not yet found these partner particles, the mathematics remains persuasive, pointing to symmetries that may have governed the universe long before it expanded into stars and galaxies. A fifth fact sharpens the line. Symmetry breaking may itself be the spark of creation. Imagine a perfectly balanced state, like a pencil standing on its tip. It cannot stay balanced forever. A tiny nudge, random, quantum, inevitable, sends it falling, and once it falls, one side becomes chosen over another. That fall is symmetry breaking. In cosmology, this kind of fall can release energy, drive inflation, or even ignite a big bang. The break is not destruction, it is transformation. The universe as you know it may exist because symmetry was broken at just the right moment. Let's pause and reflect, because philosophy is humming under these equations. If the deepest truth of nature is symmetry, then the story of creation is the story of imperfection. Perfection cannot endure, it is sterile, frozen, incapable of becoming. Only when perfection fractures does life, time, and structure emerge. The great irony is that imperfection creates beauty, and the first imperfection may have been the choice of one symmetry over another. That is why some physicists say the most important fact about our cosmos is not what symmetries exist, but how they break. Another fact joins this chorus. The Higgs field, discovered through its boson in 2012, is the very agent of one such breaking. Without the Higgs, particles would remain massless, unable to clump, unable to form stars or people. Its existence tells us that the fabric of reality chose a specific state, a lowered energy valley, where particles acquire mass. That choice may have been the defining moment when a universe like ours became possible. If symmetry had not broken in that way, no atoms would bind, no chemistry would spark, no thought would exist to wonder what came before. And yet another fact steps forward, subtle but crucial. Symmetry may not only have broken, but may have been restored in the distant past. At higher energies, all the distinctions we know today could melt away into one unified interaction. If you roll back the cosmic film far enough, you approach that unity. But if you roll it back further still, you may find that the unity existed before expansion, as the ground state of a pre-bang cosmos. In that sense, our beginning is not the origin of symmetry, but its fall, the moment order fractured into variety. Let philosophy rise again here, because the mirror of symmetry is a mirror of ourselves. Just as the universe began by breaking perfect balance, humans define themselves not by perfection, but by divergence, by choices that create identity. If everything remained symmetrical, every possibility equal, every path identical, there would be no story. Life requires asymmetry, just as the cosmos does. You are the product of broken balances, in your biology, in your thoughts, in the history of your species. The very fact that you can ask what was before is because symmetry broke, and in the breaking time began. So gather the facts from this chapter. Laws of physics are rooted in symmetry. Forces unify at extreme energies. Electroweak unification is proven in experiments. Supersymmetry offers a deeper mirror, and symmetry breaking may be the engine of creation. Each fact reveals that before the bang, the universe may have existed in a perfectly symmetrical state, waiting for a break to release the energy that would become everything. And now the cliff sharpens once again. If the cosmos can reset by breaking balance, then perhaps what we see as a singular beginning was not unique at all. Perhaps the universe contracts, balances, breaks, and expands again, over and over in eternal rhythm. That rhythm is the next path before you, the cosmic bounce, where collapse becomes birth, and beginnings are simply new phases in a cycle without end. You've seen how symmetry breaks can unleash the energy of creation, turning balance into birth. Now the story carries you toward an even larger rhythm, one that suggests beginnings are not singular events at all. Let's open this chapter with our next big fact. The Big Bounce hypothesis proposes that our universe is not the first, but one in a chain of expansions and contractions. Instead of emerging from absolute nothingness, the cosmos may have collapsed from a previous state, rebounded and expanded anew. The bang, in this picture, is not a birth, but a bounce, the moment when contraction flipped into explosion. The second fact steps in like a steady drumbeat. General relativity itself allows for contracting universes. Nothing in Einstein's equations forbids a cosmos from shrinking, its galaxies drawn together by gravity, until densities rise beyond comprehension. The question is, what happens at that crunch? Classical physics would predict a singularity, a wall of infinite density, but quantum gravity, the physics not yet fully known, may replace the singularity with a bridge. Instead of a dead end, you get a bounce. That is why so many cosmologists believe the crunch may not be final, but transitional. Here comes a third fact, sharpened by new models. In loop quantum cosmology, space itself is quantized, built from tiny units of geometry. When densities grow extreme, the discreteness of space exerts a repulsive effect, preventing true singularities. In this framework, a contracting universe naturally rebounds, turning collapse into expansion. Our Big Bang, then, is simply the aftermath of a previous contraction. Space never disappeared, it compressed and re-expanded, like a spring released. This is one of the most mathematically concrete ways to describe a universe before the bang. The fourth fact flows directly from this. If a bounce occurred, it could explain the low entropy of the early universe. During contraction, disorder might be smoothed out, spreading so evenly that the rebound begins in a near uniform state. This resets the arrow of time, allowing entropy to rise again with each cycle. The puzzle of why our universe started so ordered could thus be resolved, not by coincidence, but by repetition. Each cycle scrubs the slate clean, preparing the cosmos for another age of stars and galaxies. Another fact deserves its place here. Bouncing cosmologies are not mere speculation. They leave potential fingerprints, such as subtle non-Gaussian patterns in the cosmic microwave background, or distinctive gravitational wave signatures. If detected, these patterns would distinguish a bounce from inflation-only models. Scientists already analyze sky maps for precisely these anomalies. The data remain inconclusive, but the search is alive. Each new telescope sharpens the possibility of testing whether our universe has lived before. Pause, and let philosophy add its voice. The bounce transforms death into continuity. Instead of an endpoint, collapse becomes part of a rhythm, like an inhale followed by an exhale. The stars burn out, the galaxies converge, and instead of final darkness, a new dawn follows. This is not just mechanics, it is a redefinition of mortality on the grandest scale. To think in terms of bounces is to accept that endings may be illusions, preludes to transformations you cannot yet see. The sixth fact joins with a whisper of humility. Bounces do not erase mystery. Even if contraction leads to expansion, we must still ask what set the cycles in motion. Why is there a rhythm at all? The bounce may answer what came before the bang, but it may not answer why there is something rather than nothing. That deeper question still hangs, reminding us that even cycles must have a context, a stage upon which they unfold. And now, a seventh fact arrives, carrying a provocative thought. Some bounce models predict asymmetry between cycles. Each rebound may not be identical. Constants of nature, distributions of matter, or quantum states might shift slightly from one era to the next. If so, the universe itself evolves, not by chance but through iteration. Every cycle is not just a repetition but a variation. Over infinite cycles, constants may drift, structures may refine, and perhaps even life emerges more readily in some cycles than in others. This cosmic evolution makes the bounce more than mechanical, it makes it creative. An eighth fact follows, bold yet grounded. Black holes may play a role in these cycles. As the universe contracts, black holes merge, swallowing structure, smoothing irregularities. In some models, the singularities of black holes connect to the bounce, feeding their energy into the next expansion. In this sense, the darkest abysses of one universe become the seeds of the next. What looks like destruction from within is nourishment from beyond. The cycle is fed by collapse, balanced by rebirth. Here is the final fact of this chapter, carrying you toward the cliff. The Big Bounce is not merely speculation about the past, it reshapes the future too. If cycles are real, then the distant fate of our cosmos, the cooling, the fading, the dark, will not be the end. One day, trillions of years hence, contraction could return, galaxies could fall inward, and the stage would be set for another rebound. The universe you inhabit now would become the soil of the next, and in that next universe, perhaps beings will ask the same questions, wondering what came before their bang, never suspecting that it was you. So gather the truths of this section. The universe may contract and rebound, quantum geometry may prevent singularities, entropy may reset with each cycle, and the cosmos itself may evolve across infinite ages. Each fact reimagines the bang as a bounce, a moment in rhythm rather than an origin in time. And so you stand again at an edge. If cycles are possible, then memory itself may survive across bounces, carried in patterns, numbers, or laws, which leads to the next step, the universe's memory of itself, encoded in patterns of recurrence that may be the oldest facts of all. You've followed the rhythm of contraction and rebound, the cosmic breath of the big bounce. Now the focus sharpens on something more elusive, the idea that the universe may carry a kind of memory, faint but enduring. Let's begin this section with our next big fact. The universe retains imprints of its earliest moments in patterns we can still measure today. The cosmic microwave background is one such record, the fossil light of infancy. But some researchers suggest the cosmos holds deeper memories, stretching even across cycles, encoded in the very rules that shape matter and energy. The second fact steps in quietly but firmly: physical constants. The speed of light, the strength of gravity, the charge of the electron may themselves be the universe's memory. They are not arbitrary, they are values handed down like heirlooms. If our universe arose from a prior cycle or bounce, those constants may carry forward, slightly altered or preserved intact. Each age of the cosmos would then inherit parameters from its parent, a form of continuity across expansions. The constants become memory's script, telling the next universe how to behave. Now a third fact arrives, colored by geometry. Certain mathematical structures, like the ratio of cosmic density to curvature, may also serve as carriers of memory. If one universe contracts with a particular geometry, its imprint could survive the bounce, influencing the shape of the next expansion. Geometry, in this sense, is not merely space, but the record of what came before. To measure curvature today is to glimpse echoes of older universes, their shapes lingering in the lines of ours. Here comes a fourth fact, woven with both physics and poetry. Entropy itself may function as memory. Each cycle might reset to low entropy, but tiny asymmetries can endure, creating subtle fingerprints. These asymmetries would guide the development of structure in the new universe, much like faint scars that influence growth. If true, the rising entropy we experience is not just disorder, it is the unfolding of a story whose prologue lies in a cosmos long gone. The second law becomes not only a rule of thermodynamics, but a book of history written in disorder. A fifth fact deepens the intrigue. Penrose's conformal cyclic cosmology proposes that certain black hole collisions in the far future could leave marks that pass into the next aeon. The idea is that when black holes evaporate, their information stretches infinitely, and in the transformation from one universe to the next, faint rings of radiation may survive. Detecting such rings in the CMB could be evidence that our universe remembers its predecessor. If confirmed, this would be one of the most direct clues that the cosmos itself has continuity beyond a single bang. Now philosophy joins in, because memory is not only a physical process, but a metaphor for identity. If universes can inherit constants, geometry, or imprints, then each cosmos is not wholly new, but the child of its predecessor. Just as you carry DNA from ancestors, the cosmos may carry parameters from older ages. Identity is preserved, not in detail but in structure. This transforms before from a void into a lineage, a genealogy of realities stretching backward through uncountable bounces. The sixth fact appears as a bridge between the micro and macro. Quantum fluctuations may be another form of memory. If fluctuations cross the horizon during inflation, they freeze, becoming classical imprints. Some theories suggest that in a bounce these frozen patterns could reappear, shaping the seeds of galaxies in the next universe. It would mean that the arrangement of matter you see today carries whispers of tremors that shook not just this cosmos, but perhaps earlier ones. The galaxies themselves would then be fossils older than our universe. The seventh fact comes with cautious precision. Not all scientists agree that such memory is possible. Many argue that bounces erase all information, creating true resets. Others insist that small imprints could survive in subtle forms. The debate itself is part of the story, whether the cosmos is forgetful, always starting clean, or whether it remembers, passing along traces like messages in a bottle. The question remains open, and its resolution could reshape our understanding of origins. Now let philosophy enter again, because the parallel with human life is striking. Memory is both fragile and persistent. Individuals forget, yet species remember through culture, through language, through evolution. If universes behave in similar fashion, then perhaps forgetting and remembering are woven into reality itself. To live in a universe that remembers is to inhabit continuity. To live in one that forgets is to inhabit pure beginning. Both possibilities are profound. Here comes the eighth fact, guiding us back to observable science. Researchers have searched the CMB for anomalies that might be signatures of earlier aeons. Some report concentric circles, others dismiss them as noise. The debate is unresolved, but the act of searching makes the cosmos a detective story. Each faint ripple, each unexpected alignment, could be memory surfacing through the oldest light. If those memories exist, they may already be written in the sky, waiting for sharper eyes to read them. The final fact of this chapter ties the threads together. Whether through constants, geometry, entropy, or fluctuations, the idea of cosmic memory transforms the bang from an origin into a continuation. Instead of nothing exploding into something, it becomes something evolving into more. And in that vision, you see that our universe is both new and ancient, new in its details, ancient in its inheritance. The cosmos may be young in years but old in lineage. So gather what you've heard, constants as heirlooms, geometry as scars, entropy as story, black holes as messengers, and the possibility that galaxies themselves carry echoes older than time. Each fact deepens the suspicion that the universe remembers more than we think. And once again you reach the edge. If universes carry memory, then they may also be selected, not randomly, but through patterns that favor survival. Which brings you naturally to the next step, the bold idea that universes evolve like living things, shaped by selection across cycles. That is the secret waiting in the next chapter. You've just walked through the possibility that universes carry memory, inheriting constants, geometry, or scars from previous ages. Now the path leads into an even more daring idea that universes don't just remember, they evolve. Let's begin with our next big fact. Some physicists, most notably Lee Smolin, have proposed cosmological natural selection. The idea is simple but radical. Universes can reproduce through black holes, and each child universe inherits slightly different laws of physics. Over countless generations, universes that produce more black holes reproduce more often. The result is evolution, not of life, but of universes themselves. Here's the second fact, stated plainly. If this theory is true, our universe may be fine-tuned not for life, but for black holes. The conditions that allow stars to form, collapse, and create black holes may have been selected over cycles of cosmic reproduction. Life, under this view, is not the main outcome, but an accidental passenger, a side effect of the laws that favor black hole abundance. It is humbling to consider that our very existence may be incidental to a larger reproductive logic of the cosmos. A third fact sharpens the point. This theory provides an explanation for the apparent fine-tuning of constants. Instead of invoking a designer or pure coincidence, cosmological natural selection treats fine-tuning as the result of trial and error across countless universes. Just as biological evolution explains the complex adaptations of life without needing foresight, cosmic evolution could explain the delicate balance of physics without requiring a singular miracle. Fine-tuning becomes inheritance, sculpted by success over unimaginable time. The fourth fact emerges with philosophical weight. In this view, universes become participants in a larger Darwinian process. They are not static stages, but evolving actors, generating variation and passing traits forward. Each bounce, each black hole birth, is not just a reset, but a continuation of a larger lineage. Our cosmos may not be the first, nor the last, but simply one generation in an ongoing evolutionary tree. The Big Bang is then a birth cry, not of the universe, but of a universe within an endless family. Now let's bring in a fifth fact, grounded in science. Smolin's theory makes predictions. If universes are tuned for black hole production, then changing the constants of physics slightly should generally result in fewer black holes, not more. This means our universe sits near an optimal point for black hole abundance. While difficult to test directly, This principle gives the theory a degree of falsifiability, setting it apart from more speculative multiverse ideas. It isn't just philosophy, it's a scientific hypothesis open to challenge. A sixth fact steps in, linking back to life. Although black holes may be the main goal, life could still thrive in such a cosmos, precisely because conditions favorable for black holes, long-lived stars, stable matter, complex chemistry, are also favorable for complexity and biology. The coincidence is profound. The same laws that maximize black holes also maximize stars like our Sun, planets like Earth, and the chemistry of DNA. Evolution of universes and evolution of life intersect, not by intention, but by necessity. Pause here, because philosophy insists on being heard. If universes evolve, then reality itself is alive in a sense, not in consciousness, but in process. Life as we know it becomes a fractal expression of a deeper pattern. Selection, inheritance, variation. You are not separate from cosmic evolution, you are a microcosm of it. Just as cells reproduce and species adapt, universes too may reproduce, their traits carried onward. The same logic that makes you possible may make all existence possible. Here comes the seventh fact. The concept of cosmological evolution may help explain why the universe is just right for complexity. Instead of invoking chance in a multiverse or cycles without selection, this model suggests a cumulative process. Universes poorly suited for structure fade quickly, leaving no descendants. Universes suited for complexity thrive, spawning generations. We live in one of the successful ones, not because it was chosen, but because it reproduced well. An eighth fact expands the horizon. If universes evolve, then perhaps new physics itself evolves. Constants drift slightly, equations shift, and what we call laws of nature may not be immutable. They may be emergent properties, stabilized by selection. This means what we consider timeless truths could themselves have histories. Gravity, electromagnetism, quantum rules, they may have changed across cycles, converging toward forms that maximize reproduction. Laws would then be less like commandments, and more like habits, shaped over ages. The ninth fact brings us back to observation. While direct evidence is elusive, hints could come from the specific values of constants. If small variations would indeed decrease black hole production, that pattern would support the theory. Cosmologists already run simulations to explore how constants affect star and black hole formation. The very fact that our constants seem so finely balanced remains one of the strongest motivations for exploring this evolutionary lens. Finally, a 10th fact closes the chapter. Cosmological natural selection reframes the question of before the Big Bang. Instead of asking what preceded our universe in isolation, we ask what lineage it belongs to. Our cosmos may be one branch in a tree that stretches back indefinitely. Each branch blooms, collapses, and seeds another. The universe you inhabit is both unique in its details and ordinary in its role as one generation in an endless chain. So gather the facts of this section. Universes may reproduce through black holes, fine-tuning may result from selection, predictions can in principle be tested, and the very laws of physics may have histories. Each fact paints a cosmos not as static but as evolving, shaped by a larger process across cycles. And now the cliff rises again. If universes evolve and each cycle carries variation, then perhaps there is no final law, no ultimate design, only ongoing transformation, which leads you to the next step, quantum cosmology itself, where uncertainty and probability don't just shape particles but entire universes, each flickering into possibility before and beyond the bang. You've just stepped through the bold vision of universes evolving, each generation shaped by selection through black holes. Now we shift into the even more delicate terrain of quantum cosmology, where probabilities themselves become the foundation of existence. Let's begin this chapter with our next big fact. In quantum theory, the universe can be described not as a single history, but as a superposition of many possible histories at once. Just as a particle is described by a wave function that encodes probabilities of being here or there, the cosmos itself may have a wave function, a grand equation of all possibilities before the bang ever crystallized into a single reality. Here comes the second fact. One of the most famous attempts to capture this idea is the Hartle-Hawking no-boundary proposal. According to this model, the universe did not begin with a sharp edge in time, but emerged smoothly out of a quantum state without boundaries. Instead of asking what came before, this model suggests there was no before at all. The universe simply transitions from a timeless quantum state into classical expansion. It is not creation from nothing, but creation from a wave function that required no prior edge. The third fact flows from this. Quantum cosmology proposes that universes can tunnel into existence from quantum fluctuations. Just as particles can appear briefly in a vacuum before disappearing again, entire universes might emerge spontaneously out of quantum foam. Some vanish quickly, collapsing back into possibility. Others stabilize, expanding into full-blown realities like ours. In this view, the bang is a quantum fluctuation that got stuck, inflated, and survived. Our universe is simply one of the rare fluctuations that lasted. Now a fourth fact enters, highlighting a profound twist. Probability amplitudes in quantum cosmology are not about where particles are, but about which universes exist. Every possible initial condition carries a probability. Some universes are far more likely than others, shaped by the balance of energies and the rules of quantum gravity. The fact that our universe exists at all implies that its initial conditions, however improbable they seem, had enough amplitude to become real. Existence itself is an outcome of probability. A fifth fact steps in, more unsettling but deeply logical. The many worlds interpretation of quantum mechanics suggests that every quantum possibility becomes real in some branch of reality. If applied cosmologically, this means every possible universe exists, not just inflationary bubbles, but every mathematically permitted universe flickers into being. In that case, before the bang is not a single event, but an infinite branching structure where all beginnings occur. Our bang is one leaf on an eternal quantum tree. Pause here, because philosophy presses close. What does it mean to live in a universe born of probability? It means existence is not a guarantee, but a chance. The cosmos is not a story with a predetermined outcome, but a lottery of possibilities, and you live in one of the winning tickets. The strangeness is not that you exist, but that probability allowed a universe stable enough for stars and life. The question of before becomes a question of likelihood. Why this history among the infinite others? Here comes the sixth fact, speaking with humility. Quantum cosmology is still an unfinished language. We do not yet have a full theory of quantum gravity that unites general relativity and quantum mechanics. Without it, our models of tunneling universes or no boundary states remain partial. But even partial models reveal something extraordinary, that the question of beginnings can be asked in mathematical terms, not only in metaphors. We can write equations that describe possible pre-bang states. That is already a revolution. The seventh fact connects this to observation. If universes tunnel or emerge from quantum states, they may leave signatures in the distribution of fluctuations we see today. Some versions of the no-boundary proposal predict slight differences in the spectrum of cosmic microwave background fluctuations. Detecting these differences is extremely difficult, but not impossible. The fact that we can even imagine testing quantum cosmology is itself remarkable. It transforms the question, what was before, into a scientific hypothesis. The eighth fact widens the view. If quantum cosmology is correct, then time itself may not be fundamental. Instead, time could be emergent from correlations in the wave function of the universe. In the timeless quantum state, all possibilities coexist. What you experience as the flow of time is simply the unfolding of correlations between subsystems, like the rhythm of one clock compared to another. Before the bang, there may have been no ticking at all, just a timeless quantum whole waiting to unfold. A ninth fact follows with philosophical depth. In this sense, the universe is not a story unfolding in time, but a timeless structure in which all stories already exist. The bang was not the beginning of existence, but the beginning of our experience of time. What you call before was not earlier, it was timeless. The mystery then is not why the universe began, but why you find yourself moving along one particular thread of possibility within it. And here is the 10th fact to close this chapter. Quantum cosmology reframes the question of origins from why is there something instead of nothing to why does this particular possibility exist among all possible ones. It shifts the focus from creation to selection, from nothingness to probability. The bang was not a singular miracle but a weighted outcome of a quantum field of possibilities. Our existence is not impossible, it is simply improbable, and probability itself may be the ultimate law. So gather the truths of this chapter. Universes may exist in superpositions. The no-boundary proposal erases sharp beginnings. Tunneling fluctuations can birth new cosmoses. Many worlds extend possibility to all outcomes, and time itself may be emergent, not fundamental. Each fact places probability at the heart of existence, suggesting that before the bang may be a timeless sea of possibilities from which our cosmos crystallized. And now the cliff rises again. If quantum cosmology describes probabilities of universes, then what about the strange role of consciousness? After all, in quantum mechanics, observation seems to matter. Could awareness itself be linked to the fabric of reality, shaping or selecting the universes that unfold? That is the daring path we take next. You've just explored the strange terrain of quantum cosmology, where universes may exist as probabilities, and time itself may be emergent. Now we turn to a more delicate frontier, one that connects directly to us. Let's begin this chapter with our next big fact. In quantum mechanics, observation seems to play a role in how probabilities become realities. A system described by a wave function exists in many states at once, until an observation collapses it into one outcome. This mystery has haunted physics for nearly a century, and when applied to cosmology, it opens a daring possibility. Consciousness may be tied, however subtly, to the unfolding of the universe. Here comes a second fact, stated with care. The observer effect does not necessarily mean human minds create reality, but it does mean that measurement, the act of interaction, determines outcomes. At the smallest scales, existence is probabilistic until it is observed. Extending this logic to the cosmos, some interpretations suggest that the very act of observation by conscious beings may help define which universe among many possibilities becomes realized. Awareness, then, is not a latecomer to the universe. It may be woven into its fabric from the start. A third fact enters with a stronger link, the anthropic principle. It reminds us that the universe must be compatible with conscious observers, because we are here to notice it. On the surface, this may sound trivial, but in practice it becomes profound. Out of countless possible universes, we exist in one that allows consciousness to arise. This fact ties the existence of observers to the structure of reality. Before the bang, then, you may imagine a vast ensemble of possibilities, with only some fertile enough to grow consciousness. That fertility becomes a filter, shaping which universes are experienced. The fourth fact brings philosophy close to physics. John Wheeler once suggested the participatory universe, where observers help bring the cosmos into being by their presence. According to this view, the universe is not a machine running independently of awareness, but a feedback loop where observation and reality co-create. In Wheeler's words, we are not just in the universe, we are part of the mechanism that makes it real. The bang, then, is not only an expansion of matter and energy, but also the eventual flowering of observation. Without observers, the universe would remain probability. With them, it becomes history. Now, a fifth fact speaks softly, but with gravity. Neuroscientists have found that consciousness itself depends on complex integration of information across the brain, especially within networks like the thalamocortical loop. This tells us that awareness is not magical but emergent. If so, consciousness may be another kind of cosmic memory, arising whenever conditions permit. That means consciousness need not be unique to our era or our cosmos. In a universe before the bang, or in another bubble, wherever complexity evolves, awareness could bloom again. Reality, then, may not only repeat matter and stars, it may repeat awareness. The sixth fact arrives from quantum theory's edges. Some interpretations, like the many minds or consciousness causes collapse views, suggest that awareness is fundamental, not emergent. According to these, the act of observation by a mind is what crystallizes one branch of reality from many. While controversial and far from proven, this view places consciousness as a root ingredient of existence, alongside space, time, and energy. If true, then before the Big Bang must also include awareness in some form, timeless and waiting, just as quantum possibilities did. Pause here, because philosophy deepens the tension. What does it mean if consciousness is not an accident, but an ingredient? It would mean that reality is incomplete without awareness, that the universe was always destined to awaken, not by miracle, but by necessity. Awareness becomes the cosmos, recognizing itself. The bang, then, is not only physical birth, but also the stage upon which awareness could eventually emerge to look backward and ask what came before me. Here comes the seventh fact, the entanglement principle of quantum mechanics, where two particles remain linked across space, has been extended metaphorically to suggest that minds and cosmos may be entangled too. Though not literal physics, the metaphor highlights something real. Just as entangled particles collapse together, observers and universe cannot be separated. You are not an external viewer peering in. You are part of the wave function, participating in its unfolding. Before the bang, perhaps all was entangled as one timeless whole, waiting to differentiate into universe and observer alike. An eighth fact grounds us again in science. The field of quantum cognition applies quantum principles to decision-making and thought. Human minds sometimes follow probability patterns more aligned with quantum mathematics than with classical logic. While this does not prove consciousness is quantum, it hints that awareness and probability may be more connected than we once thought. If your mind mirrors the same logic that governs particles, then consciousness may be an echo of the same quantum rules that shaped the pre-bang state. A ninth fact steps in carefully. Cosmologists debating the wave function of the universe often face the question, who or what observes the universe as a whole? If no external observer exists, then collapse must happen internally, through decoherence between parts of the universe itself. But others argue that observers within the universe play a crucial role. Either way, the act of choosing one history over another remains a central mystery. Consciousness may not create universes, but it may be inseparable from how universes crystallize into experienced reality. And here is the 10th fact to close this chapter. While the role of consciousness in cosmology remains speculative, it opens a profound bridge between physics and philosophy. If awareness is emergent, then it is the cosmos remembering itself through us. If awareness is fundamental, then it was present even before the bang, woven into the very possibility of existence. Either way, consciousness cannot be dismissed. It is the mirror the universe holds up to itself, and through that mirror, we glimpse not just where we are, but what may have been before. So gather the truths of this section. Observation shapes outcomes. The anthropic principle ties awareness to structure. Wheeler's participatory universe links observer and cosmos. Neuroscience shows awareness as emergent, and some interpretations place consciousness as fundamental. Each fact converges on the same possibility. Before the bang, consciousness was not absent, it was either latent or timeless, or destined to arise. And now the cliff sharpens once again. If consciousness and the universe are intertwined, then perhaps the deepest clues of what came before lie not in telescopes but in the mathematics of probability itself. For mathematics does not only describe reality, it may be reality. That is the next path, the universe as a mathematical structure, and what that tells us about existence before the bang. You've just explored how consciousness might be woven into the fabric of existence, not as an afterthought but as a participant. Now we move toward a different lens, one that sees the cosmos itself as mathematics embodied. Let's open this chapter with our next big fact. Max Tegmark's mathematical universe hypothesis proposes that reality is not merely described by mathematics, it is mathematics. Every equation, every structure that can exist in math exists physically as a universe. Our cosmos, with its particles and laws, is one mathematical structure realized. This suggests that before the bang, the universe already existed in abstract mathematical form, timeless and complete. Here comes a second fact, subtle yet profound. Mathematics doesn't depend on human invention. Prime numbers would exist even if no minds counted them. The ratio of a circle's circumference to its diameter would still be pi, whether or not anyone drew a circle. If mathematics is timeless, then the universe as a mathematical structure is timeless too. That means the bang was not the start of existence, but the transition from a timeless mathematical possibility into a realized physical form. The before is mathematics itself. The third fact follows with clarity. Physics has consistently revealed that the deeper you dig into nature, the more it looks like math. Quarks and leptons are organized by group theory. Space and time bend according to differential geometry. Quantum states live in abstract Hilbert spaces. None of these are inventions. They are discoveries of patterns already written into reality. This convergence suggests that math is not just a tool, but the underlying fabric. If so, the bang did not create laws, it simply revealed a structure that was always there. A fourth fact steps in like a quiet echo. In this mathematical view, every possible consistent set of equations describes a universe. That means there is not one cosmos, but all possible ones. We live in one mathematical structure because it permits stability, complexity, and consciousness, but countless other structures exist out there, each as real as ours. Before our bang, then, there was not nothing, but an infinite landscape of mathematical possibilities waiting like a library of universes. The fifth fact adds a startling implication. If mathematics is reality, then nothingness is impossible. Even if no physical space existed, mathematical truths would remain. 0 would still equal 0. 2 plus 2 would still equal 4. These truths are eternal, independent of time. That means existence is inevitable. Something must exist, because mathematics cannot not exist. Our universe is one manifestation of this inevitability, the translation of timeless truths into physical form. Now philosophy joins, because this thought reshapes meaning. If the universe is mathematics, then to understand reality is to learn its equations. Science becomes not just a human endeavor, but the cosmos remembering itself in symbols. Every theorem, every formula, is not invention but recognition. To ask what was before the bang is to ask which mathematical structures allowed the transition into time and space. The answer lies not in matter, but in logic. Here comes a sixth fact. Gödel's incompleteness theorems remind us that even mathematics cannot be fully self-contained. There will always be truths that cannot be proven within any system. Applied to the cosmos, this suggests that no single universe can contain all truths. Each is partial, each incomplete. If all mathematical structures exist, then our universe is one theorem among many, each expressing part of reality. The bang becomes the opening of one proof in an infinite archive. A seventh fact emerges from physics itself. The success of predictive mathematics is uncanny. Einstein's equations predicted gravitational waves a century before we detected them. Dirac's equation predicted antimatter before it was found. This eerie accuracy suggests that mathematics knows more about the universe than we do. If the cosmos were not mathematical at its core, such predictive precision would be inexplicable. It is as if the universe cannot help but follow the logic of numbers. An eighth fact expands the view. If the universe is mathematics, then time may be an illusion of perspective. A mathematical structure is complete all at once, like a sculpture. To beings inside, events appear sequential, but from the outside, the entire history exists timelessly. Our bang, then, is not the start of a story, but one part of an eternal structure. Before and after are simply directions within the sculpture of reality, not true beginnings or endings. Pause now, because philosophy presses close again. If all mathematical structures exist, then our universe is not privileged. It is simply one island in an ocean of infinite forms. This humbles the notion of uniqueness, but it also enlarges meaning. The very fact that we can grasp mathematical truths places us in resonance with the cosmos. Our minds are tuned to the same order that underlies reality. We are not separate from the math. We are expressions of it. Here is the ninth fact, tying the arc back to cosmology, inflationary theory, quantum mechanics, and string theory, all lean on advanced mathematics, whose structures existed long before physicists discovered them. This continuity suggests that the bang did not invent these laws. They predated it as mathematical truths. The bang merely realized one branch of the mathematical tree. Others remain unrealized to us, but no less real in the grand ensemble. And finally, the 10th fact. Seeing the universe as mathematics reframes the question of origins from why did something appear out of nothing to why this structure among all possible ones. The bang becomes the activation of one solution in the infinite space of math. Our existence is a choice made not by an agent but by logic itself. So gather the truths from this chapter. Reality may be mathematical at its core. Math is timeless, existing before the bang. Every consistent structure may describe a universe. Nothingness may be impossible, and time itself may be part of a completed mathematical object. Each fact points to a startling idea. What was before the bang was mathematics itself, eternal, inevitable, and unbounded. And now the cliff edge appears again. If the universe is mathematics, then perhaps it is also information, bits and codes, patterns and computations, which leads us naturally into the next and final section, the digital universe, where reality is a simulation or computation, and the bang is the booting of the ultimate program. You've just stood inside the idea that mathematics itself might be the foundation of reality, a timeless structure that existed before the bang. Now we take our last step, a step into the possibility that the universe is not only mathematical but computational, that reality itself may be a kind of code running on a cosmic substrate. Let's begin with our next big fact. The digital physics hypothesis suggests that the universe is made of discrete information, bits rather than continuous fields. Just as your computer screen looks smooth but is built from pixels, the universe may appear continuous but is actually woven from finite informational units. If so, the bang was not an explosion of matter, but the initialization of a program. Here comes the second fact, one that grounds this vision. John Archibald Wheeler, one of the most influential physicists of the 20th century, coined the phrase "it from bit." His idea was that every particle, every field, every force ultimately derives from binary choices, yes or no, 1 or 0. Reality itself, at its deepest level, is information. Before the bang, then, reality may have been pure data, timeless and structureless, waiting for computation to run. A third fact now unfolds. If reality is information, then physical laws are algorithms. The equations of physics are not just descriptive, they are instructions, rules that update the state of the system, step by step. The expansion of the universe, the formation of galaxies, even the evolution of life, could then be seen as computations running on the substrate of space-time. The bang would be the moment the code began to execute, a cosmic boot-up sequence that continues to run across billions of years. Here is a fourth fact, surprising but essential. Some researchers believe the Planck scale, the smallest meaningful length and time units, may be evidence of discreteness. If the universe has a minimum resolution, it behaves like a digital simulation with a finite pixel size. Space and time are not infinitely divisible, they are quantized. This supports the view that the universe is not a continuous analog field but a digital fabric. Before the bang, then, you could imagine those pixels in their ground state, waiting for initialization. The fifth fact takes us deeper. The simulation hypothesis suggests that our universe might literally be a simulated environment created by a higher intelligence. If computation can produce universes, and if civilizations advance far enough, then simulated realities may vastly outnumber base realities. Statistically, some argue, we are more likely to be living in a simulation than not. The bang, in this view, was the moment the simulation started, when the servers were powered on. Before it, there was no physical space, only data waiting to be executed. Pause here, because philosophy insists on balance. If we are in a simulation, then the meaning of before changes radically. Before the bang may mean before our program ran, in the realm of the simulators. Yet whether simulated or not, the laws of our cosmos remain valid within it. Falling in love, building civilizations, studying physics, all are real experiences, because reality is defined by the rules we live in. A simulated cosmos is still a cosmos. The distinction may be philosophically deep, but experientially irrelevant. Now a sixth fact sharpens the science. Quantum mechanics itself resembles computation. The act of measurement is like reading an output. Superpositions resemble parallel processing. Entanglement resembles shared memory. Some theorists even suggest that the universe runs like a quantum computer, simultaneously exploring many states before collapsing to a single outcome. If true, the bang was not just a physical event, but the first clock cycle of a universal quantum processor. Before it, there was no execution, only potential instructions. Here comes a seventh fact. Cosmic structures themselves resemble information networks. Galaxies form in web-like filaments that mirror neural networks. Black holes, paradoxically, store information on their surfaces in bits proportional to their area, not their volume. This holographic principle suggests that the universe itself encodes information two-dimensionally, projecting the world we see. If the cosmos is holographic, then before the bang may have been an informational surface, flat and timeless, from which three-dimensional space emerged like a rendered image. An eighth fact adds more intrigue. Experiments with high-energy cosmic rays have searched for signs of pixelation in space-time, tiny irregularities that would reveal a digital grid. So far, no such irregularities have been found, but the search continues. If such evidence appeared, it would suggest our universe is indeed a finite computation, not an infinite continuum. That would be the first experimental hint that before the bang might mean before the program started. The ninth fact brings philosophy back into the frame. If reality is computation, then information never truly dies. Bits may change form, but they are conserved. This aligns with the physics of black holes, where information cannot be destroyed, only scrambled. It also means that in some sense, every moment, every memory, every configuration of the universe is preserved. Even if universes reboot, the data remains encoded somewhere. Before our bang then, there may have been not emptiness but an archive, a cosmic database holding the information of older worlds. And now the 10th fact closes this chapter and the journey itself. Viewing the universe as computation unifies many threads. Symmetry breaking becomes a change in code. Quantum fluctuations are random seeds in a program. The multiverse is the set of all computations that can run. Consciousness is information integration, and the bang is not an explosion but an initialization. Line 1 of the cosmic algorithm. What came before was not chaos but possibility, the blank state of a processor before the first calculation began. So gather the final truths. The cosmos may be digital at its core. Wheeler's it from bit frames reality as information. Physical laws act like algorithms. Space-time may be pixelated, and the bang may have been a boot-up. Each fact points to a universe that is not merely physical, not merely mathematical, but informational, a computation unfolding across time. And now you stand at the final edge. Across this long journey, you've followed 101 hidden facts, from cosmic bounces to multiverses, from entropy to symmetry, from black holes to consciousness, from mathematics to computation. Each has whispered an answer to the question, what was there before the Big Bang? Perhaps cycles, perhaps infinities, perhaps probabilities, perhaps information itself, and perhaps the truest answer is that all these visions are facets of the same mystery, that existence never began, it only transformed, again and again. You've now completed the journey through 101 hidden facts, each one a window into the question of what might have existed before the Big Bang. The path has carried you through physics and philosophy, through myths and mathematics, through cycles, probabilities, and possibilities so vast they reshape the very sense of beginning. And now the rhythm changes, the search for answers quiets, and what remains is the resonance of wonder. Think of the vastness you've just traced, not as a puzzle to solve tonight, but as a landscape to rest within. You've seen the universe as memory, as evolution, as symmetry, as probability, as consciousness, as mathematics, and as code. Each perspective is incomplete on its own, but together they paint a mosaic not of certainty, but of possibility. Notice how the mind feels after such a journey, no longer racing toward conclusions, but circling gently as if orbiting a star. Every question leads not to an end, but to a wider horizon, and in that widening there is calm, because the search itself becomes enough, the mystery itself becomes a companion. You do not need to hold all the details in memory, they are like constellations. Some points you will recall clearly, others will fade into the background, yet the shape will remain. What stays with you is the feeling that creation is not a single event, but an unfolding, that time is not a line, but a rhythm, that existence is not fragile, but deeply, endlessly fertile. So as the last words dissolve, let them settle like dust in starlight, let them linger not as noise, but as quiet assurance. You live inside a cosmos that remembers, evolves, computes, and dreams, and tonight it has shared a little more of its secret history with you.